do be here and interact with speakers and other colleagues. So we've tried, each year we try to make things a little different based on the feedback that we have got. So we have tried to arrange some sessions in a thematic way. I've also been trying to engage with the sectional committees so that they also hold some meetings so that everybody who does not get a chance to speak here can speak to their peers in a more focused manner. The other change that we have this year is that the dinner tonight will be at the Raman Research Institute, which is a little bit down the road. Of course, given the horrible Bangalore traffic, one has to allow some time to reach there. But it's a very nice venue, and I hope you will all enjoy it. So once again, welcome. And without further ado, let's get on with the program. And yeah, that's all.
Good morning, everybody. We will begin this event with a special lecture by Professor Pradeep Datta, and it is my pleasure to introduce him to this audience. Professor Pradeep Datta is affiliated with the Interdisciplinary Center for Energy Research at this institute, at the Indian Institute of Science, Bangalore. And his research focuses mainly on thermal energy storage, advanced cooling technologies, and phase change and adsorption-based energy systems. Professor Datta earned his bachelor's degree in mechanical engineering at IIT Kharagpur, his master's degree at IIT Madras, and a PhD also in mechanical engineering at Columbia University in New York. He is a fellow of several very distinguished societies, the ASME, that's the American Society for Mechanical Engineers, the ASTFE, the AUTSE, and all 4 national science and science and engineering academies in India. This academy, ISC, as well as INSA, NASI, and INAE. He has received several prestigious honors. He is a distinguished alumnus of both IIT Kharagpur and IIT Madras. He is a recipient of the J.C. Bose National Fellowship, and he's been named an outstanding teacher by the INAE. He has also served as a president of the Indian Society for Heat and Mass Transfer. At this academy, the Indian Academy of Sciences, he was elected as a fellow in 2012. So today he will tell us more about digital transformation and environmental sustainability. We look forward to your talk.
You can keep this one. It's on. Yeah, and okay, this is nice. Yeah, thank you, Dr. Meena, for the nice introduction. And I would like to thank the Academy of Sciences, especially Professor Raghavan, for giving me the opportunity to deliver this lecture. This is a special lecture, and it's special for me also, because normally I'm not used to giving, public talks which could be of general interest. I'm more used to giving research talks in my own domain, but when Professor Raghavan asked me, can you give a talk which is of general interest, if I pick something out of my research basket, I can relate to only some of you. So I was wondering what I would pick as a possible topic. So I chose this, digital transformation and environmental sustainability, because I feel that, as a scientific community, we need to have a wider perspective of what's going on in this world, which has implications in various fields, including geopolitics. So, we are all aware of, what, digitalization is about. We use mobile phones, we use, laptops, tablets, and using these devices, we connect to the internet, we do video conferencing, We do Google search and then AI tools. Um, and we are also, as a scientific community, conscious about what kind of environmental footprint that this field can have. So, and more so because this change that is happening is very rapid. And with this rapid change, it is giving rise to demand, or huge demand, in mainly two kinds of commodities. One is critical minerals and the other is energy. Critical minerals because the hardware needed for the digitalization, especially the high power AI chips nowadays, they need critical minerals to do certain special functions. And that includes also mobile phones, it includes electrification of transportation sector, batteries and so on will need special materials which are called the critical minerals. And to power these systems, we need enormous amount of energy for data centers and the network infrastructure that is created around everything. So with that background, let me move ahead with the topic. And what I would do is maybe we can dim the lights a little bit so that the picture, is that all right with everyone? Yeah, thank you. So let's read the title from in the reverse order, sustainability. So what do we mean by sustainability? We have some idea about it. And sustainability has many kinds of definitions and many kinds of understanding. The official definition of sustainable development is given by the United Nations. It just is a very simple definition that development should meet the needs of the present without compromising the ability of future generations to meet their own needs. So very simple definitions which we all understand. But human beings need to progress, and we have our needs and the ambitions which are growing very rapidly again. For that, we would need resources which are energy, water, land, and food. And when we talk about the sustainability, environmental sustainability, we are talking about air, water, soil pollution, ozone layer depletion, global warming as the three pillars which we need to address. Now, to begin with, let's see from an energy point of view, what is the primary energy consumption by source. This is a 2024 data. And what it shows is that if you see 2024 data, oil, gas and coal, the fossil fuel still is much larger than wind, solar or other renewables, even though we have made tremendous progress in this. And there is, you will hear that so many gigawatts and terawatts of renewable energy being generated, but don't go by the nameplate capacity only, because something like solar, it may say 1 gigawatt, but it may be giving the peak performance only 2 hours a day or 4 hours a day, and sometimes in some days nothing at all. So this is the actual picture that is there. So now let's look at it by country. The biggest consumption is China, and then United States. China, because that's a factory of the world, and they make almost everything that we are using in the rest of the world. So just let's keep this in the background right now. We'll visit this later scenario. And since we are talking about fossil fuel still being the largest source of energy, so this is the scenario with the oil reserves, if you see. And something which is this maroon color, like dark red, it is in terms of billions tons. Something of a lighter shade would be much less than that. And where do these exist? If you see that the largest reserves are Venezuela and Middle East. So you can connect the dots later. I will come back to it. Okay. Now, what are the sustainability issues? One issue is about the depletion of the fossil fuels, and the other is the climate crisis. At one time, the depletion was, like in the 70s, more concern was about the depletion of the resources. But now, the climate crisis has taken over, especially with this rising CO2 increase, and that is leading to global warming and other effects that we are all aware of. And to address these, there are policy agreements and frameworks. So the key international agreement, there are many agreements. This Paris Agreement is what we refer to always, and that's the guiding agreement that we are still abiding by. And there are supporting frameworks which have been created, including the IPCC, UNFCCC. And under this, there is a COP, Conference of the Parties which have engaged, all the parties means all the countries which have engaged and signed or pledged that we need to mitigate the climate change or address the issues. So these meetings are held every year. So, based on the COP meetings, which is working under the Paris Agreement, there are limits that are set. That is 1.5 degree limit of global warming. So to contain the damage that is happening. And then there are 2030 targets which came up at COP 28 and beyond. So the focus in 2030 target, the focus was on the renewable energy and efficiency. And then there was 2035 target, which is again re-emphasizing the 1.5 degree limit, and 2050 target, which is net zero, that we will not use fossil fuels at all. Everything will be renewable or clean energy. So let's keep that in the background. So based on that, there are some decarbonization routes. Decarbonization means we will not produce CO2 or reduce it as much as possible. So the decarbonization routes, one is the generation of energy would be, as we all know, solar, wind, hydro, nuclear, etc. And the electrification of the transport, including home heating and industrial operations. And what it turns out that we need also storage. So therefore, we need a mix of electricity and clean fuels. So there is a terminology called the power to X, P2X, which means that you can use renewable power, but you need also something like a fuel. So there's the indirect storage of electricity is via conversion into fuels, beginning with hydrogen, and then you can reform it to other fuels which can be more easily used. So the key thing is basically the energy storage. That's the success. That will lead to the success. But the electricity storage in batteries in small scale, it works out fine. That's why in large scale, it is a little bit difficult because that will also cause environmental issues with so many batteries. So green fuel is also looked at as large scale, and thermal storage is the other one. So these are basically as far as storage is concerned. Now let's come to the main theme of today's talk, which is the digitalization and the growth and what kind of environmental impact it can have. So these are just some tidbits and snapshots of how things are changing. For instance, the carbon footprint of the digital world is creating about 1.5 gigatons of CO2 equivalent. And the raw material extraction for the critical minerals and other materials, just a snapshot, if you see, a 2 kg computer, it requires extraction of about 800 kg of raw materials. Then there are data centers. I'll come to this in more details later on again. And if you see that in 2024, data centers have been consuming 415 terawatt hour of power. And in 2030, it is estimated to be 945. And there is also accompanying water usage from 0.2 to 1 liter per kilowatt hour of energy that is used in the data center. And then there are these infrastructure devices, how it is growing. If you see, the 5G coverage is expanding from 2021 is 25% now, is projected to be 85% by 2028. Then IoT devices, this is how it is increasing. So this is just a tidbit snapshots, I would say, just which is painting a complex picture of the digital economy's environmental impact and how quickly things are changing. And very difficult to even keep track of all that. Now, but at the same time, there are positive impacts, which we all use. We use computers and computation, simulation, and all the tools which would be used for our research and efficiency of engineering activities and industries. So resource efficiency, supply chain, everything becomes more efficient when we use digitalization. And then environmental monitoring, weather prediction, everything is aided by this one. So there is a positive impact of it. And also in circular economy, many things we are able to simulate and predict. So therefore, we are able to take better decisions in this one. So all is not bad. So I am painting the other side as well, which would be beneficial. But what are the challenges and negative impacts? Energy and water consumption, the growing demand for the data centers and the AI systems, as I was just discussing. They are increasing energy consumption in those sectors. Then environmental waste, how to recycle them, and I'll come to that in more detail, how difficult it is to recycle many of these materials, especially in which is used in the digital infrastructure and devices. And the other thing that we need to worry about is a rebound effect. Many times what happens is something more efficient comes in the market, and then we tend to use more. Something like an LED lights when they came. It turns out, we're looking at even the India data, before the LEDs came, the power consumption by lighting alone was much smaller than the power consumption for lighting now that we see after the LEDs came, because we use multiple lights now. We use more of it because we are not paying, we are paying less for the energy, right, that is consumed, or less energy is consumed because of that. So that's called the rebound effect, which is also happening. So, and the nature of digitalization is also changing very rapidly, because the high speed processing, online transmissions, and our expectations are also more now. The computations and processing have shifted to the cloud. Then digital platformization, because there are business platforms like Amazon, Uber, they use it in a shared form, many of these resources. Then cognitive changes, big data analytics, machine learning, AI, all that it is getting into our daily lives, right? And virtuality. Growing use of augmented reality and virtual reality. So all that is changing very quickly. Like shifting to the cloud, for instance, many things that we use at one time, even 20, 30 years back, most of the processing that was done, it was done on our device. If it's a computer, all the processing was done there. But nowadays, we can use a mobile phone and hardly any processing is done there. So there are apps which are basically interfaces. We send information it goes to some cloud or data processing center, and the information comes back and we get it. So nothing is done actually, or virtually nothing is done actually on our devices. So basically we are relying on the cloud. So many times we don't even realize, what we are doing to the environment by just Googling something or using a ChatGPT even to get a simple answer. Should I what should I buy for my groceries today? Something like that. We use ChatGPT today. Anyway, so then what is the nexus between the digitalization and environmental sustainability? We call it also twin transition, because while we are transforming to a digital economy, we are also trying to push our economy towards a low carbon economy. Till one point, they were parallel because they were serving the same objectives. Because we have used digitalization towards environmental sustainability by reducing paper consumption, energy consumption, and so on. But today it is becoming interdependent, and not only that, it's competing and conflicting. And that's what I want to bring in front of all of you today. The digital tools, of course, they are increasing the efficiency and resilience. Digitalization itself must be made more environmentally sustainable. So that's the objective that we should have. And the other thing is that both sectors are, from a material point of view, they are using the same rare earths or critical minerals and metals and inputs, if you see, because our photovoltaic system or renewable energy also uses many of these materials. At the same time, from a consumption point of view, for in our digital world also, we are competing with the same materials and resources. So there's a resource competition, and this is also leading to significant changes in international trade and the geopolitical challenges that it is bringing up. So how to assess all these? There are tools, and those tools are called the life cycle analysis, because you cannot just look at a product and judge whether it's good for the environment or bad for the environment. We need to look at life cycle, means that right from the minerals that we are extracting all the way to recycling of at the end, after the end of life. So there are basically phases. There is a build phase of a device, there is a use phase, and then there is a end of life phase. So that is we are looking at also the production, supply chain. Now what has happened is, now most of the digital economy until now has remained linear, which means that it is not belonging to the circular economy as yet, because we are producing, and at the end, so many mobile phones I have used. I don't think I have recycled any of these yet. They die and somewhere they disappear, even laptops and other things, right? So it has remained mostly linear, which is not a good news. So we need action, which is reduce, reuse, and recycle. This LCA, there is a standardization procedure of how to calculate, because there are so many different ways of calculation that sometimes we can project a thing to be very rosy. We can give a rosy picture, and sometimes very dark picture also, depending on where you are coming from and who is funding the research. So that standardization is an important thing, and it encompasses multiple criteria beyond the greenhouse gas emission. So if you look at the ICT sector infrastructure, basically there are three elements in it, major elements in it. One is the data center where the processing happens. Then there is a network infrastructure, and there is an end user devices. End user devices is what we are most familiar with, our phones, laptops, and IoT devices. And they are all interrelated and interconnected in a digital way. So coming to the life cycle analysis, as I was mentioning, we have a production phase where we are extracting and refining the raw materials and then manufacturing that device. Then there is a use phase, and this is where the energy is used in our devices. That gets taken into account. And in the use phase, energy use and water consumption and the greenhouse gas emission, these are the issues that we look at. And then finally the end of life phase, which relates to the circular economy, that how it can be recycled. Okay. Now coming to one thing at a time, we will focus mostly on the production phase and the use phase, because the end of life phase is another domain which I will not touch upon, that is more complex. In the production phase, if you see your smartphone composition, the metals amount for about 45%, and these are the other materials which are there. And there are critical minerals in this because of the functionality that it has to do. And even there is growing demand not only in the ICT but also in the EVs and solar panels, those critical minerals, right? So now I don't know if you are aware what is in your smartphone. And let's find out what you are carrying in your pocket. And this is the periodic table, which we are all familiar with. So all the colored ones, the colored boxes, are basically in your pocket. Okay. And gradually some of the others may also become colored. And if you are looking at other devices like EV motors and photovoltaic panels and everything, then some of the other boxes will also become colored. So now the dynamics of all this is that there is an exponential growth in internet and data traffic. There is higher computing power, better mobile technologies, and greater consumption of digital devices and hardware. So that's increasing in the building of ICT data infrastructure, and all this is resulting in increased demand for minerals, metals, and materials, right? So, and the energy part is also there, right? So, as far as minerals and metals are concerned, see, it is a finite planet, and we are extracting. When we are extracting, what is happening is that if you look at that, also is increasing from 16% in 2022 to 34% in rebound in 2020. I mean, yeah, this is global exploration budgets are rising, especially in these countries where the resources are, and now the tech giants are looking at even deep sea mining and space mining. There are trillions of dollars of budgets that are being put now there, and people are investing money. So that's the kind of challenge and uncertainty that we are going to, because so much of demand is being created. So now to look at how the global concentration of minerals and metals exports are, if you see that mostly it is concentrated in Africa, some in Latin America, Australia, and some other countries. China also has a share in this one. And so these are the places where most of the those minerals and materials are. But if you look at processing, because it's just not enough to extract the materials, you need the processing technology. And where it is most dominant, the dominant processing is actually being done in China, which is the blue color. So any of these materials, the share of mineral processing is dominated by China, that you see. So it's not just the having the materials, but also the materials technology for processing. And so the impact of the production phase, which we are going through right now, associated with mining, the greenhouse gas emission, water use, pollution of soil, and other effects. And there are social impacts also, because these are creating issues about people's health and safety, communities, particularly indigenous people. You have to rehabilitate them somewhere else, and the working conditions which people are in now. So that's a different domain which I will not go into, but that's a social issue which we see. And the other effect that is happening is a mineral depletion. Now, why we are talking about mineral depletion? It's a finite world. Minerals are still there. Only problem is that minerals, when we talk about something mineral or an ore, it is in a form of concentrated. A concentrated nature. So when the concentration is high, we are calling it as a high exergy, because you can make use of it very easily. But as we are using it, we are unearthing it and then using it, it goes into so many devices, billions of devices, they are getting distributed. So just a thermodynamic analysis shows that you need, so the exergy is actually decreasing, or we can also say entropy is increasing. So it is more and more difficult that even though those minerals are there, it's difficult to bring them back again to use. So that is where the problem lies. We need enormous amount of energy again for any kind of recycling, because the way it's distributed in the photovoltaic panels or in our mobile phones and all, it is almost impossible, or it needs a very, high degree of purification again to bring it back into circular economy. So that's why we call that the recycling is very energy intensive. So now coming to this use phase now, that was the build phase. Now the use phase, we are consuming energy and water, especially in the form of data centers. And that is leading to greenhouse gas emission, because the power that is required for the data center will have to come from somewhere. And the carbon intensity can vary by regional energy grid composition. And the cumulative footprint, we are talking about billions of connected users devices. Okay. So with that background, let's look at now how these devices are consuming power. These devices are consuming power. If you see in the desktop will be quite large. This is in terms of watts, right? And your mobile phone will be the least. Okay, but talking about the rebound part, you see that your 17-inch cathode ray tube monitor used to consume about this much of power at one time, but now with all these LED monitors and all, the sizes have become much bigger. So we are now actually exceeding what we were consuming earlier. So that's an example of a rebound effect. But of course, we are gaining quite a bit in terms of functionality and other things. Global ICT greenhouse gas emission analysis, if you see in these, that user devices, so this part is the use phase and this color is the embodied or the build phase. Right. And if you see in the case of data centers, it is showing a small amount, but I studied a little bit deeper into this one, and the main reason is that the first generation, second generation of data centers, they have almost consumed all the available green energy that is available, that is carbon-free energy they have. So therefore, the footprint right now, as far as carbon emission is concerned, is showing small, but they have used up right now. Now, the future energy generation has to speed up in terms of renewable energy or clean energy generation to keep up with it. But the actual energy consumption is much higher than what we see over here. Okay, and if you look at the greenhouse gas emission by the device type, the smartphones especially will be very little use phase, and most of it is in the build phase. But for the other devices, it can be the other way around. Okay. Now the last part of it is now looking at, let's deep dive into the data center and look at the sustainability part. There's a huge amount of electricity demand. There's a cooling and water usage and clean energy trends. For instance, the water usage, the direct water use for evaporative cooling can reach about nearly 1 liter per kilowatt hour of energy that is used in a data center. Now, what we mean by a data center, I will just quickly go over this. See, this is one of the configurations of a data center. There are many other configurations. These are basically cabinets where the servers are kept, and they are the ones which generate heat, and is the chips inside the servers that are generating the heat. So we have a cooling system. This is called computer room air conditioning cooling. So this is an air-cooled example, and that the cold air will come and then cool these racks, and the hot air will go back to this air conditioning system. And this air conditioning system again is cooled by a refrigerant or a chilled water system. So this is a refrigeration unit, and this is finally the heat has to be released into the environment through a cooling tower. And if it's a cooling tower, that is where the water is consumed, because it's evaporative cooling. Now, if you're wondering, how am I connected with with this kind of a topic, this is where our research funding comes from. This is also one place, and also in the renewable energy that is used to power these systems. Okay, so with that background, let us look at the quantification of the sustainability indices as far as data centers are concerned. One is called the power usage efficiency or effectiveness, power usage effectiveness, which is what is the total facility power that is required versus the IT equipment power. IT equipment power is when we say a data center is 1 gigawatt, that means it is consuming this much. But for cooling also, you need additional power. So that's where the total power comes in, and this is obviously greater than 1. How much greater than 1 is what we are looking at. And then water usage effectiveness is that how much of water we are using divided by the IT equipment power. And so these are basically the indices which are used, and the other index which is used, how much of footprint that it is occupying. So the rack density, especially with AI growth, they are also concerned about how much of footprint and real estate it is occupying. So in the cooling technologies and water strategies, there are air-cooled systems where zero water will be required. But in the air-cooled system, evaporative cooling is not used, so you need a huge footprint of cooling if it's a dry cooler. So that amounts to real estate and also other capital expenditure. So liquid cooling is more preferred, and water cooling, especially for the cooling tower, is preferred. So water consumption is something which is unavoidable at the moment, right? And there are also circular strategies where we can recycle the water or capture the water from the cooling tower. So that will reduce the environmental footprint. So now the growth of the data center energy consumption, if you see that in 2024, it's about 415 terawatt. By 2030 estimated it is 945, and it is exponentially growing, because we are only seeing the tip of the iceberg as far as AI is concerned. We have barely started using it. That's what the predictors are saying. So, but where are the data centers are mostly located? They are mostly located in US and China. And what is the kind of response that we are having now as far as the environmental footprint is concerned? I will come to, I'll just skip this part. The critical question is, okay, what is the kind of response that it is happening? And so I'll just give you two case studies, what kind of policies they are bringing in. But before that, let's look at also that the data center build cycle is only about 2 to 3 years, whereas your renewable energy generation and transmission cycle, the infrastructure build-up is much larger. So therefore, there's a mismatch of time scale as far as demand and supply is concerned of clean energy. So the two case studies, one is Ireland, where already about 22% of their electricity is going into powering data centers, and it is projected to become more than 30% very soon. So they are concerned, so they have some kind of a policy which they have introduced now in terms of capping, or they have to go through some scrutiny before they can build up new. The biggest response is in US. I don't know how many of you are aware that actually there is almost like a protest going on in many of these states, if you see. So anti-data center referendum passed in Wisconsin. So these are very, this year's news, all these are. Then the alarming environmental impact in terms of heat islands happening, around the data center, because these are gigawatts of heat that are coming into the cities that is being released in a small space. So as far as protests are concerned and policies that are being formulated, and if you see, these are basically they are passing bills which are banning or pausing the data center build-up. So this is not the usual red and blue political divide of the US, but all the red ones are actually where the new policies are coming into the picture, which would restrict the entry of data center into some of these states and cities. So the Indian scenario, we are lagging behind in that one, but we are very excited in building up, because there's so much of investment that is coming in. So we are gladly accepting them, and the projection is quite high, but we have not yet understood what is the environmental footprint as far as India is concerned. So I'll end my talk by bringing in this question, posing this question: is it sustainable or not? Right. So if you look at now, there are these tech giants who are going to space or propose to go to space to build data centers, right, with million satellites. And they are also looking at mining in space. Now, these are very ambitious projects. These are very ambitious thoughts. Now, why are they doing it? They are doing it so the moment you go to space for both mining critical minerals as well as the powering the data centers in space, which means that there is that compulsion is showing that they understand and they accept that it is not environmentally sustainable on this earth. That's why they are going outside. And of course, later on, just last 2 months back, SpaceX now admits that it is not environment. I mean, they said it's not economically feasible to go to space for these data centers, but they are not yet bothered about or not addressing the issue of environment about it. But anyway, so also I will end the talk by saying that, going back to the slide which I showed earlier, that this is the present energy as far as renewable energy is concerned. So if the demand for clean energy is doubled in the next 5 years or 10 years, there's no way that we can meet from here. This can't be scaled up. So we have to rely on the fossil fuel as far as this energy demand is concerned. And that is the reason, or you can connect the dots and see why we are fighting wars on oil still right now, right? And especially by countries which are trying to maintain or establish supremacy in the AI field. Thank you very much, and I hope I am able to. Yeah.
We have a couple of minutes for a few questions.
Yes.
Ask a quick question. I've read in different places that these data centers, in order to reduce the cost or other kinds of energy requirements for cooling, they're going to places like Antarctica, sinking a ship and building a data. Is that true? That will have a huge environmental impact as well.
Absolutely. So there's a desperation now to go under the sea, go to Antarctica. In India, it may be going to the Ladakh. First of all, it's not so easy because you also have to carry the data there. That infrastructure is also impossible, but I agree with you. It is, yeah. Yes.
What is the future of green hydrogen?
Future I would say is bright. It's only a question of reducing the cost of production so that it is competitive. Right now, that is a barrier. And the other is transporting the hydrogen, and especially in mobile devices. And also, conversion to other fuel is also being thought about. Like instead of hydrogen, it could be ammonia, it could be any other devices, or any other fuel which can be stored easily under normal pressure. Right. So the storing of the hydrogen is also an issue in mobile devices like the cars and vehicles.
Excuse me.
But otherwise, I think future is bright that way.
Good
Yes.
morning. Actually, I have a question. We are hearing that China is actually building data centers inside the sea, right? So, and of course, that is also not environmentally feasible,
Yes,
because it will affect the marine life. But according to you, what do you think is better, using the fresh water to cool down those data centers, or building it in the sea?
Okay, the building it in the sea is mainly because it's a colder, or year round you get a same kind of temperature as far as the cooling environment is concerned. It is not that they are using seawater that way. So, fresh water is obviously it is not feasible. But if you dump this heat, as I think the same question was asked, if you dump the heat into the sea, it's going to cause other environmental issues. Right? Even 1 degree change in a local area, it can kill many marine, habitat.
One last question.
Yeah.
Very nice talk. Very previous question. If you have to transport heat from the data center in space, how do you do that? There is nothing over there.
It's a radiation sky cooling, basically, what we use from Earth also. It will be more efficient over there, radiation, but even that needs a huge amount of area. We have even back of the envelope calculation is showing that for a 1 gigawatt data center, you need between 2 to 4 kilometers of total area. 2 to 4 square kilometer of total area in terms of capturing the heat from using the photovoltaic panels and also radiating the heat out. So, and that's why now they are saying that it is not economically feasible. Yeah, you're absolutely right, Professor Joshi. Yeah.
Thank you very much. I think there are many more questions from the audience, but in the interest of time, we should close this session. Please join me in thanking Professor Pradeep Datta.
Thank you. And I'll be available during tea break and all, so any questions will be there. But I'm not an expert in everything in all this. Only a small part, we work on our research. But thank you very much.
Session chair? Oops, so this thing seems to have got chopped on the side.
Okay, start. Good morning, everyone. Welcome to the next session. In this session, we have two talks from the fellows. The first one is Professor Subrata Mukherjee from IISc Bangalore, professor in the Department of Physics. He has earned his PhD from Princeton and then postdoc at UC Berkeley. And he's been working in the theoretical condensed matter physics. So, Professor Mukherjee, please go ahead.
Thank you very much. I'd like to thank the organizers for inviting me to speak at this meeting. It's a real honor for me to do so. I'm going to tell you about the flow of electrons in certain metallic systems, which is more like the flow of a fluid like water through a pipe, rather than the flow of electrons in more conventional metallic systems like metallic wires. For some reason, the title of my talk seems to have got chopped off on this slide. The full title is Electron Hydrodynamics when Electrons in a Wire Flow like Water Through a Pipe. So just to set the stage for what I'm going to be talking about, so let's just consider these two kinds of flows. So the flow of electrons through a conventional metallic wire and the flow of water through a hollow pipe. So there are, of course, superficial similarities between these two kinds of flow. So both of them involve setting up a steady current due to a gradient of something. And in the case of the metallic wire, the gradient, of course, is a gradient of the voltage. In the case of water through a pipe, it's a gradient of pressure. And the current which is set up is, of course, of different things. So in the case of a wire, it's a current of electrons. And in the case of the pipe, it's a current of water droplets. So these are the similarities. You have a steady current which is set up by the gradient of something. But then what are the differences? And so there are, of course, differences. So as I said, one difference is the quantity in which you're setting up the gradient, voltage in one case and pressure in the other case. It also turns out that the relationship between the current density and the gradient is a little different in the two cases. In both cases, it's a linear relationship. There's a constant of proportionality. In the case of electrons flowing through a wire, it's the familiar Ohm's law. And this constant of proportionality is the electrical conductivity. And this is an intrinsic property of the material that the wire is made of. Now, in the other case, there is a similar linear relationship between the current density and the pressure gradient, except that it turns out that the constant of proportionality is not really intrinsic. It actually depends on the dimensions of the pipe, in particular, the radius of the pipe is proportional to the square of the radius. And the other quantities are intrinsic to the fluid that's flowing, water in this case. So those are the differences. And you can ask, well, why do you have these differences? And it turns out that the differences arise because of the microscopics of the flow, or more specifically, the way in which the particles which are flowing are actually interacting with one another and with other things. So when it comes to electrons flowing through a wire, it turns out that the momentum of the electrons is actually not conserved in the bulk. So as the electrons are flowing through the wire, because the wire is made of some material, the electrons actually interact with the material. And it turns out that the momentum of the electrons is taken up by either the vibrations of the ions that make up the metal, what are called phonons, or by impurities that can exist. So these can act as sinks for the momentum of the electrons. The electrons, of course, are colliding with one another, but that collision conserves momentum. So that is not a momentum sink. On the other hand, if you look at water flowing through a pipe, then because the pipe is hollow, there isn't anything inside, you only have collisions among the fluid droplets in the bulk, and there is no momentum loss. They just exchange momentum among one another, but there is no momentum loss of the fluid. And so that sort of turns out to be the main reason that the flow is different in the two cases. The other big difference is that if you look at the velocity profile, if you look at the velocity of the fluid as you go along the cross-section of the wire in this case and the pipe in this case, in the first case, when you have electrons flowing through a wire, that velocity is essentially constant. Whereas if you look at a fluid flowing through a pipe, there's a gradient in the velocity, with the layer of the fluid in contact with the surface of the pipe, essentially stationary, and then the velocity increases as you get to the center of the pipe and then decreases again. So there's also a difference in the velocity profile, which ultimately arises because of this issue of momentum conservation in the bulk in this case and not in that case. Okay. So you can ask the question, if not for any other reason, just for intellectual curiosity, is there any practical situation in which you can actually get electrons in some kind of a metal to flow the way that a fluid flows through a pipe? And so, of course, you can think about it, you can idealize the situation, but in a practical situation, it turns out that it has to do with length scales. And so if you're looking at electrons which are flowing through a wire, then there are different regimes of flow that are possible depending on what the operative length scales are. And so if you have a situation in which you have these electrons bouncing off impurities or of these lattice vibrations, then that is sort of the conventional situation in which you get Ohm's law, and which is also called diffusive flow. And the operative length scale in that case is this L diff, which is the mean distance for the scattering of the electrons of phonons or impurities. Now, you can also have a situation, which I'm not really going to be talking about, in which the electrons that are flowing through the wire are mainly bouncing off irregularities in the walls of the wire, something that's called ballistic or Knudsen flow. And it turns out that the operative length scale in such a situation is the radius of the wire. And then finally, if you want electrons to flow as water does through a pipe, it turns out that the operative length scale is this length scale LEE, which is the mean distance between electron-electron scattering events, the mean distance that an electron travels before it collides with another electron. Now, in any situation, all of these length scales are present, but as I said, the important thing is which one is the operative length scale, or which one is actually the smallest length scale in the problem. So if you can somehow engineer a situation in which this particular length scale, the length scale that has to do with how much the electron travels before colliding with another electron, is much smaller than the other two length scales, then the flow is essentially momentum conserving, and the electrons are going to flow like water does through a pipe. Now, in conventional metals, you're usually in this regime in which this diffusive length scale is the smallest one. So if you want to engineer this kind of flow, which is called hydrodynamic flow, in a metallic system, then the important thing is to get to this regime. And so how do you do that? So again, I apologize for the fact that this image seems to have covered some of the text. But the main thing is that you need a very, very clean sample, and so clean that the other length scale, which has to do with the amount, the length that the electron travels before colliding with impurities, is very, very large, because you have a very small density of impurities. So having an ultra clean sample is extremely important, so that this is the operative length scale. And synthesizing a sample like that was almost impossible till about a decade and a half ago, when people started making ultra clean samples of various two-dimensional materials, the most significant of which is graphene, which I guess many of you have heard of. And graphene is just basically a one atomic layer thick sheet of carbon atoms. So it's a pure single layer of carbon atoms. And it turns out that you can actually make this ultra clean, so clean that you can be in this regime. All right, fine. So the question is, how do we know if we are actually in this regime? What is the signature of this kind of flow? And it turns out that you can, in principle, even image the flow and see this velocity gradient that I showed you in one of my earlier slides. But a much more striking feature of this hydrodynamic flow in graphene is a violation of something called the Wiedemann-Franz law. So the Wiedemann-Franz law is a very important law when it comes to the transport of electrons in conventional metals. And what it is basically a relationship between the electrical conductivity, which features in Ohm's law, and the thermal conductivity, which features in heat transport in what's called Fourier's law. So these are these two transport coefficients. And the Wiedemann-Franz law tells you that the ratio between these two transport coefficients divided by temperature is a certain combination of fundamental constants. And that's what's observed in conventional metals. And so the import of this is that it essentially tells you that the carriers of heat and charge in a conventional metal are not only the same, but they're also scattered in the same way. So that, in some sense, is the physical content of this law, which is observed in most conventional metals. And it turns out that in graphene, when you're in this hydrodynamic regime, there's actually a very striking violation of the Wiedemann-Franz law. So you can measure this quantity, which my colleague Arindam Ghosh in the physics department has done in this paper. And you can compare it to what you would expect for a conventional metal. And you see that you can have a violation which is almost 3 orders of magnitude large. So this is a striking signature of the transport in the system not being of the conventional metallic type, and in fact actually being of the hydrodynamic type. And so you can ask, well, why does this happen? What is the essential physics? So to understand the essential physics, one has to realize that even though these electrons are moving in a very clean system, they're still moving in an environment of a certain sort, in a crystal environment. Now, it turns out that if you want to think of the motion of these electrons, if you think of these electrons as particles which are moving, if they were moving in free space, and you wanted to think of them as classical particles, then they would just obey Newton's laws of motion. So these are just statements of Newton's laws of motion. And I have, in this second law, included a force which could come from an applied electric field. Remember that the electrons are charged, and also a force which could come from an applied magnetic field, which was the Lorentz force. Now, it turns out that when you're looking at electrons moving through a crystalline material, right, because they're not moving in free space, there is a way in which these equations have to be modified. So the electrons are really not classical particles, they're quantum particles, they're waves. And so if you want to think of them as particles, you actually have to think of them as combinations or superpositions of waves, and the kinds of waves which are allowed to exist in a crystal. And these waves are what are called block waves. So the electrons, you have to think of the electrons when they're moving in a crystalline environment as particles which are made up of these block waves. And when you do that, it turns out that these equations have to be modified, and they are modified in a pretty interesting way, mainly this one. So you have a modification which looks like this. So instead of the velocity just being equal to the momentum divided by the mass, which is what you conventionally have in Newton's laws, you have something else here. You actually have this quantity, where E of P is what's called the dispersion, or in a certain sense is the allowed kinetic energy that the electron can have in this crystal as a function of its momentum, and that kinetic energy does not have to be equal to p squared by 2n. So this is what's called a dispersion relation, and it just comes basically from the fact that you have a crystal with a crystal structure. Then you also have the second term, which really has no analog here. This is something that's called an anomalous velocity. And so it's a velocity which depends on the rate of change of the momentum, and this other quantity here, which is called a Berry curvature. And this comes from the basic nature of these block waves. The form of these block waves actually gives you this Berry curvature. So there are these two very important modifications of the equation of motion of an electron when it flows through a crystal. And it turns out that the behavior that I showed you earlier can be explained because of this modification. So in graphene, the Berry curvature is equal to 0, so you don't need to worry about the second term. But you do have a dispersion which looks like this instead of p squared by 2m. And this is like the dispersion of a relativistic particle. And you can see that there's a plus and minus sign. So in some sense, you can have both a positive and a negative kinetic energy, which have to be interpreted as the energies of particles, electrons, and what are called holes, which are the analogs of, if you like, antiparticles in high energy physics. And so in the native state of graphene, you have neither any particles nor holes. And then when you increase the temperature, it turns out that you can actually get particles and holes. But again, in the native state of non-zero temperature, you have an equal number of them. They have opposite charges. And so then it turns out that when you apply a voltage gradient to set up an electrical current, the electrons and the holes move in opposite directions. And if momentum is conserved in the system, right, and these are moving in opposite directions and they're sort of completely symmetric, the total momentum is 0. And so if you switch off the electric field now, you can in principle degrade this current while keeping the total momentum equal to 0, because momentum has to be conserved, by degrading these individual currents. And so you can get a finite electrical conductivity. On the other hand, if you set up a temperature gradient to get a heat current, then it turns out that the electrons and holes have to move in the same direction. And now if you turn off the temperature gradient, but the momentum has to be conserved, there really is no way of degrading this current. So in principle, you get an infinite thermal conductivity. Of course, in practice, that doesn't happen. Things are not infinite. But it's because the thermal conductivity and the electrical conductivity behave so differently that you have this spectacular violation of the Wiedemann-Franz law, which comes from a combination of momentum conservation and this funny energy-momentum relationship in graphene. Okay, so I'll just conclude in the next couple of minutes. So another thing that I wanted to draw your attention to is the effect of the other term which I neglected, which doesn't exist in graphene. But it turns out that it can exist in other materials. And so in general, what happens is that if you have momentum conservation in a fluid, and you now look at how the electrical current and the heat current depend on gradients, then if you have momentum conservation, then there can also be a dependence on the velocity gradient of the fluid with an accompanying transport coefficient. And in addition to the electrical current and the heat current, you can also now have a momentum current which can be induced by gradients. So if you look at any standard textbook on solid state physics and you look at transport, these are the relations that you will see with these transport coefficients. But in the case of electron hydrodynamics, you have an extended set of relations with these additional transport coefficients, this one being a viscosity tensor. Okay. And it turns out that these coefficients in magenta and blue are in some sense novel coefficients which haven't really been investigated before, called vortical coefficients. And the reason that they haven't been investigated before is that you actually need to break inversion symmetry. You need to have a situation in which when you invert coordinates about the origin, the system is actually different in a certain sense for these to be non-zero, and that is difficult to achieve in a conventional fluid. And so no one really talks about these coefficients. But it turns out that in an electron fluid, because of this particular term, you can actually achieve inversion symmetry. There's a way in which you can get inversion symmetry from the nature of these electron waves in certain crystalline environments. And that's represented by this Berry curvature term not being equal to itself when you invert the momentum. So in a situation like that, you can actually get these coefficients to be non-zero, these vortical coefficients to be non-zero. And this is something that we worked out. Okay, and a last thing that I want to say is that in this situation, in electron hydrodynamics, you can also, if you look at the momentum current or the stress tensor, it turns out that the stress tensor can actually be asymmetric, unlike in conventional fluids. And that asymmetry can be attributed to the fact that there can be an intrinsic angular momentum of these electron wave packets due to this Berry curvature. So an asymmetric stress tensor typically has to, tells you that the orbital angular momentum of the fluids is not conserved. And here that's because of this intrinsic angular momentum that these wave packets have. Anyway, so to summarize, I hope I've been able to convince you that electrons in certain funny kinds of metallic systems can flow like water through a pipe. And that happens when electron-electron scattering is the dominant mechanism and momentum is conserved in the bulk. There is an experimental signature, one among many experimental signatures, which is this large violation of the Wiedemann-Franz law. And in systems with a non-zero Berry curvature, you can actually get these novel transport coefficients to be non-zero, which you don't observe in conventional fluids. So thank you very much.
Thank you, Professor Mukherjee. Yeah, we have time for a few questions.
Oh, sorry, I think there's a question. Yeah, can you speak into the mic, please?
Maybe you can.
Thank you, sir, for the talk. So my question was, when the momentum is conserved for this hydrodynamic regime, is there a practical relevance in which it changes the properties of that electron flow in the material? So will the material properties change? Is there a practical relevance for that material?
Yeah, well, so the thing is that the reason that the momentum is conserved is because of the material. It's because the material is so pure and that there aren't any impurities or any appreciable density of impurities for the electrons to scatter off, that the momentum of the electrons is conserved. It's not, in some sense, the other way around, that the momentum of the electrons being conserved is giving the material some properties. It's really more the properties of the material giving you this kind of behavior.
Ruth, I had a quick question. So, of course, if it's ultra pure, you said that the heat transport is just infinite. I guess in the experiment, because you know the concentration of impurities, there's a simple way of estimating.
So eventually, what makes your thermal conductivity finite and not infinite is the fact that you have some concentration of impurities, no matter how small that is, and also that the sample has a finite size. So you do have this effect of the boundaries where momentum is sunk. So,
is there any question? Yeah.
In the case of electron hydrodynamics, you have the quantum potential, right? Apart from the classical potential, the equation of motion, fluid dynamical equation should have a quantum force.
Okay, so you're asking what is the effect of the quantum potential or all of this? Yes. So the thing is, so I didn't tell you very much about where this dispersion is coming from. So the electrons are moving in a periodic potential, and that motion of the electrons in the periodic potential has to be considered as a completely quantum problem. And so the quantum mechanics of that problem is what is even giving you this epsilon p in the first place. So if you're thinking, if by quantum potential you mean the periodic potential considered and the quantum effects of that, so the most important place where that's going into all of this is in the form of epsilon of p. And this also, by the way, is a quantum quantity, because it comes, when I say the form of the block waves, it actually comes from the wave functions of the block waves. So that's also a completely quantum quantity.
Any other question? If there is no other question, please join me in thanking Professor Mukherjee for his nice lecture. Yeah. Let me call upon the next speaker, Dr. Ruza Mandal. She's Associate Professor, Department of Physics, IIT Gandhinagar. And her work is focused on theoretical particle physics areas. Dr. Mandal.
Okay, hello everyone. Let me first thank the Academy for the kind invitation, and I'm very glad to be here to be able to present my research work. So I'll be talking on from quarks to new physics, the lessons what we learned from beam mesons. So from the topic, you might guess that we work in high energy particle physics. So the main questions which thrive this whole field are the two, which we can summarize here. What is the universe made of, and how do its fundamental constituents interact. Basically, in this area of research, we try to explain whatever phenomena we see around us from at its very fundamental level. And so far, whatever in the quest of, say, answering these questions, whatever we have learned is actually captured in a theoretical description which is known as the Standard Model of particle physics. So I just show you here the particle content of this theory. So here we see in purple color there exist some quarks which are interacting themselves, and they are responsible to make the structure of, say, hadrons, say protons and neutrons. There exists a set of leptons, 6 of them. They are just there. Electrons, we just heard about it in the last talk. And there exist 4 gauge bosons which are shown in red. So they are basically responsible for the fundamental mediation of the fundamental forces. For example, photon is the mediator for the electromagnetic interaction. So the electricity and magnetism, all the phenomena which we know so far can be described by the interaction of the photon to the all other particles which I am listing here. Similarly, gluon is also responsible for the strong interaction, basically known as the quantum chromodynamics, how the quarks are actually inside this bounded inside the mesons. That can be described by the interaction of the gluon. And then we have the W and Z bosons, which are responsible for the another fundamental force, which is the weak force, which tells us like why the sun actually shines and how one nuclear element actually disintegrate to another element. So basically all those 3 forces can be written in this model in a quantum field theoretical description, where these interactions are written as some gauge group, or say in group theory language. So here I have just shown you the gauge group which is known as the Standard Model gauge group. And so far, this is not just a theoretical construction. We have actually seen all these particles at the experiment, including the last one, which is the Higgs boson, and that's responsible for the generation of masses for all the other fermions which are present, and also the gauge bosons in this theory. Not just these particles are seen at experiments, their properties are very well measured at experiments at per mil level. For example, the W and the Z boson properties are known very well. And over like thousands of verifications are there between the Standard Model and the experiment. So it's a remarkably successful theory to describe the world so far we know at its fundamental level. But definitely there are certain open questions which this theory cannot explain. For example, we do not know how to incorporate the dark matter, which we see the existence from the astrophysical evidences. We know that the 27% of the universe budget, which is kind of 5 times more abundant than our ordinary matter. What is its nature, how it comes, that those questions cannot be answered through the Standard Model which I am showing here. Also, we see more matter than the antimatter, although if we believe that the Big Bang was creating the matter and antimatter in equal amount, why we see such asymmetry, we do not know the answer from this theory. Also, the certain particles which are known as these neutrinos, they remain massless in this theory, but experiment has already proven that neutrinos are massive. So we need to give some reason which is kind of beyond the scope of this theory. While these 3 are some experimental clues to motivate beyond Standard Model theories, we also have some theorist prejudice, which I would say that those are listed in these last 2 points. So why the fermions? So basically the fermions are starting from, say, electrons to the heaviest one is the top one. So if we see the mass spectrum, all of them are observed at experiment. If we see the mass spectrum, there is a huge 7-8 orders of magnitude difference. And from theory side, we want to understand why there is like such a difference between the masses. So that's known as the mass hierarchy. Also the Higgs, which was discovered actually just 4th July, today is 3rd July in 2012. So we still from theory side, we cannot make its mass completely stable from quantum correction. So these are the theoretical issues of this theory. So far we are kind of standing in somewhere where we have success, we have open questions, but definitely we did not see anything directly in our experiments which are currently going on. So how do we actually proceed from here? So there are actually two ways to proceed. Definitely we need more experimental input. One way is we directly produce some new particle or just try to measure their properties at collider. So this is a picture of the Large Hadron Collider, so at CERN Geneva, so where people are actually having two proton beams colliding each other at several places. So these are the 4 places where proton beams are collided. They are actually going through this circular tunnel, and at those 4 places detectors are installed, so basically just to see what is coming out from those collision. So direct production means you increase the energy, you produce maybe some heavy particle at those accelerators and try to discover them. But however, we so far did not succeed to discover any new particle after the discovery of Higgs boson, which is already proposed in the Standard Model. There is also another way which is known as the indirect effects, for which we need basically precise measurements. So just schematically I am trying to tell you what do I mean by indirect effects. So for example, say at experiment we measure some quantity which should be unity with some 10% error. And from our theory side, the Standard Model tells us that that quantity which we measure is around 70%. So there is a mismatch between the data and the theoretical prediction. So might be possible that this mismatch is causing because of the contribution coming from any new particle. So that is kind of telling you the hint of indirect way of telling you that existence of some new particle, which is I'm just showing you here, fulfilling the gap between this data and the theory. So these are known as the indirect ways, and they can probe the energy scale, which is much beyond the scope of the direct colliders. And interestingly, this way predicted the existence of charm quark much before its discovery at the real experiment. So first slide I was showing you the full particle spectrum, like there are 6 quarks, but definitely there was no theoretical guidance to tell that why there exists 6 quarks. Those are experimental outcomes. So people already knew about three quarks, and they just observed that some ratio of some decays, like some K meson decaying to some leptons, which is coming out to be extremely tiny at the experiment. However, there was no reason from the theory side why it should be so small. This is just a typical Feynman diagram for this process. But what I mean that if you don't have the C quark, you see this contribution which is much larger than the experimental prediction, and then people came up and postulated that there must be existing some another quark which is the charm quark, and they even predicted its mass with these indirect effects, and later at Collider people looked at the charm quark at that energy scale and they discovered. So this is kind of a success story of indirect search, and that's why we can somehow get a knowledge of the energy scale at which we need to probe to directly observe anything at the colliders. And why this is possible? Because from theory side, what we do, we write everything in an effective theory. So as you know, in physics, scale is very important. At what scale you are measuring, that actually tells you what kind of theory you should work for. So the Standard Model, what I was telling you in the first slide, which is consisting of this gauge group, it might be some effective field theory, and any effect of, say, new heavy particle, those you can include in terms of some operators and coming with some Wilson coefficients which are called C. You can actually modify your theory. Say for example, the weak gauge boson Z, if you are at energy scale which is much below than the mass of the Z, then you are left with the theory which is just the quantum chromodynamics and quantum electrodynamics. So it's a much more different theory, but effect of this Z boson will be encoded in terms of another set of new operators. So this way of going back and forth in the scale is possible very much through the technique which is called as renormalization group evolution. We can do it until some scale where the perturbation theory actually works for us. So as long as we are very close to the lambda QCD scale, which is the scale where the bound states are formed in quantum chromodynamics. Basically, say protons or neutrons are formed, which is around few mega electron volt. So at that scale, all the non-perturbative physics dominates because you cannot do the expansion in the standard perturbative way. So the area where I am just working and I was trying to motivate, that actually is in between these two regions, perturbative region as well as the non-perturbative region. So here stands all the hadron decays. And in this case, one of these very interesting hadron is a B meson. So B meson is nothing but just a bound state of a B quark and any anti-quark. So it's the heaviest one so far which we know forms a bound state. And why these mesons are interesting? Because when they decay in the standard model, their decay rates are actually very, very suppressed. So they go via some quantum loops. So if there are any heavy new particles or interactions, they can contribute to this mode via the decay. We can see its effect in terms of a large set of independent measurements which are done for these modes. So here I just listed a few interesting decay modes from the experimental side. So in experiment, we have dedicated colliders to study the properties of these B mesons. So in the left, I am showing this is a collider which is known as BEL-2, situated at Tsukuba, Japan. So here people are colliding two electron and positron beams, which is at the center of mass energy of a BB bar pair. And then people are studying the outcomes or the decays of the B meson at different properties. Similarly, as I mentioned, within LHC, there is a dedicated detector which is known as LHC-B, which is also looking for all the properties of the B meson. And so far currently, what we have some interesting tensions between the data and the theory, which are known as B anomalies. So here I am just showing you one angular observable for some particular mode B2K star mu mu. And this is like where you can see the error bars are the experimental measurements and the bands are the theory predictions. So there is some mismatch between the data and the theory within certain region. Similarly, for another channel, you see that somehow the data and the theory is not matching. So somehow hinting us to go for some indirect, maybe indirect signatures for something new. And the deviations are at the level observed at 3 sigma confidence level. Okay, so if we look from the theory side, what goes into this calculation, as I said, angular observables, they depend both on short distance and long distance physics. So in the short distance, we have the Wilson coefficients, which we can calculate easily in perturbation series. And that's where all the effect of heavy particles will come. The long distance is always difficult. We need the non-perturbative techniques because there exist the form factors, because these are ultimately the bound states, the mesons are bound states and they are decaying. So while calculating the form factors, there are certain techniques which are known as light-cone-sum rule, lattice QCD, heavy quark effective theory, and tremendous effort is going since past to actually improve these form factor predictions. Not just the simple form factors, we even have certain complicated contributions which are known as non-factorizable contribution. So this is just the typical diagram I was showing you, the penguin diagram for a B2A SLL transition, which is going via Charn loop. Then I was telling you the scale of EFT which I can go from here and there using RGE. The thing is, the B decays are at the B quark scale. So we can integrate the heavier ones beyond the B scale, but Charn quark is much lower than the B scale. So those are still the dynamical degrees of freedom. And if they emit a gluon and which is ending inside the mesons, those contributions are very difficult to actually quantify because limited by the unknown QCD dynamics. So the main challenge for us is to, whenever we are comparing data to theory, we have to improve the precision of the estimates. And that's what we were trying in few of our works. So the standard, one of the very important method which calculates I will take a couple of minutes maybe. So calculates the non-perturbative things is known as the light-cone-sum rules. So here we actually write a correlation function which is based on operator product expansion. We can write the perturbatively calculable amplitude as well as the non-perturbative things are included in condensates. And we use the dispersion relation to actually connect it to physical parameters. Of course, there are limitations. We rely on some model ansatz that the ground state is actually saturating most of the spectral density, and then the Borel transformation is actually suppressing the continuum. And we also have to impose the quark hadron duality. That means beyond certain energy scale, their hadron physics is mimicked by the interaction between the quarks and the gluons. So that contribution which I was showing you, the non-factorizable one, which looks like a bit this one, with the complete amplitude, and this h mu is that contribution generated from these 4 quark operators. So we try to compute this contribution, which is a time order product of this electromagnetic current and with these 4 quark operators using the Lightcon-Sum rule. I'm just skipping all the details at this point. What caused the overall the contribution is actually causes actually a shift in the Wilson coefficient C9. So that's where all the new physics effects are there. So that's why I'm just trying to send the message that it's very, very important to distinguish the QCD with the new physics so that we are not making any mistake while identifying it. So some previous calculations, there were order 3 difference between these predictions. So recently with my student Praveen and the 2 postdocs Alam and Ipshita, we have actually computed the whole contribution including complete set of the LCDS, and we find that there is some 10 times enhancements in the non-local form factors for these channels. We have also actually improved the precision of another important key parameters which are going into the form factor calculation known as the inverse moment of LCDS. So we use the lattice data for the form factors, and we have the theory predictions from Lightcon-Sum rule, which depends on this parameter which we want to extract. And what we find in these 2 works, one is for B, another is for B sub S, that the contribution, that the uncertainty in this parameter, which is actually improved almost twice than the so far known computation, and that's why we see also another improvement in the form factor predictions. So what I am trying to send the message here is that the precision physics is very, very important when we try to compare theory with the data, and the data is like piling up a lot because both BEL2 and LHCb, these 2 colliders, will be running for at least for next 10 years. So we will have definitely the validation of discrepancies observed so far, and we will have like several decay modes. Already we have several decay modes which are measured at experiments, but we do not have any theory prediction for those. So we really need the theory community to come together and compute these complicated contributions to improve the precision. So maybe in one day the precision prediction may reveal some of the first cracks of the standard model of particle physics. So thank you very much for your attention.
Thank you, Dr. Mandal. We have time for a few questions. Yeah, there.
Thank you for the talk. My question is, CERN is going to undergo for the next 4 years a high luminosity upgrade. How do you see your field evolving with that?
Right. So, okay, my slide has been okay. It's there. So as you see here, exactly what you said correctly, we are in this long shutdown period, and after that there will be high lumin era, and this luminosity plot is for LHC-B only. That means the one which is doing the B physics, and you see like huge amount of data will be piled up, and there will be definitely the validation of the discrepancies and several new modes. So it's really a very, very interesting channel area to explore.
Any other question? Comment? Yeah, there, please.
Yeah. So I was just wondering, when you say that this might provide evidence for new particles, what kind of attributes of these particles do you assume in the theoretical models? Do you assume that they only interact via the weak interactions and EM interactions, so they just have some electrical charge and some isospin, or is there something more that you...
It depends. Like at the moment, these B decays are weak decays, so definitely they will have some kind of weak interaction, but they can have also some new gauge interactions as well. That's like depends. It's like bottom to top approach. So in the bottom, we have the EFT. From EFT, when we go for the model building, we can have several possibilities, but definitely it will be narrowed down by the data as well.
So I had a quick question. So it seems that the theoretical calculations are also pretty hard because there are some non-perturbative effects, and you mentioned lattice computations.
Right.
But are theorists sort of thinking of some other things, because lattice computations have these various finite size artifacts and things like that? So
right. So lattice is one, and another one which I was discussing is this QCD sum rule, light cone sum rules. So that's like another area. And there are several other heavy quark effective theories. Also, one can somehow combine. So lattice works in a little bit different kinematical area where I am just looking. So it's like you can combine those two with some intermediate approach as well. So there are several, like for example, heavy quark effective theory, light cone sum rules, and all those areas, which are complementary to lattice.
Any other question? If there are no other questions, please join me in thanking Dr. Mandal. I thank the Academy for this opportunity to me. Thank you.
The first one, it's a request. Please don't get your tea, coffee cups onto this side of the hall, because that's what the administration wants. And the second one is for fellows who haven't signed in yet, and those fellows who have been and associates who've been recently elected. That's a register kept right there. Please put in your entries. So see you in about 15 to 18 minutes. Thanks.
Well, good morning to all of you back from tea. It's a great pleasure to have 4 speakers in this session. So it's going to be very exciting. Firstly, let me invite Professor Prashant Kumar Das. He's a senior professor in the School of Biological Sciences at the IACA Calcutta. IASC Calcutta, many of you may not know the expansion. Indian Association for the Cultivation of Science, a very important institution. Prashant, as you get ready with your mic, he will discuss on the self-aggregated fluorescent organic nanoparticles engineered to respond to specific enzymes, allowing for highly sensitive bioimaging and diagnostic. Prashant, the stage is yours, and you know the timings.
Yes. Well, thank you, Chairperson, and also I'm really thankful to the Academy for this kind invitation and allow me to share some of the research activity which is going on in my lab at IACS, and welcome you back to the podium. So, as you could see from the title that today I aim to speak on the domain where we'll be referring to the fluorescent organic nanostructure, and that would be utilized towards sensing a cancer cells by exploiting the oxidoreductase enzymes which are overexpressed in the cancer cells, and we'll take a few examples of that. So prior to moving into that, we'd like to know why you got interested in the organic nanostructures. It's a beautiful manifestations of the self-aggregated amphiphilic molecule. And where from the inspirations came in for that? And the inspirations always come from the nature, as you all know. We try to mimic the several phenomena that's been taking place in the nature. And one of such a simple thing in the natures are the self-assemblies. There are beautiful manifestation examples are there in the nature, starting from this, chromatin structures to neuronal cells, and the basic building block of a life is a cell, and which is comprises of a cell membrane. And this cell membrane is one of the finest manifestation of self-aggregations without any forces, outside forces, is got self-assembled. And because of the presence of this amphiphilic lipidic molecule within that, which is having hydrophilic head and hydrophobic tail. And to understand the structure functions and the phenomena that has been taking place in the membrane systems, and the scientists and the researchers, they try to make things more simple. And from there, the concept came in the mind is the molecular assembly, where we try to design simpler analogs of this lipidic molecule, which can, depending on the temperature, system structures, can give rise to the formation of different manifestations of the self-aggregated structures, like a simple amphiphilic molecule having a hydrophilic head and hydrophobic tail. Depending upon the situation and structure, that can lead to the formation of micelles, reverse micelles, different microemulsions, the vesicles, which are the closest mimic of these membrane mimetic systems, and followed by the higher order aggregates like gels, and very concentrated organic nanostructures like carbon dots. And this is another fantastic manifestation of this self-assembled structure is the organic nanoparticle. So to go into today's topic, I just briefly want to mention the research activity in our lab at IACS is centered around the self-assembled organic nanostructures, where we have been working in the development of the microemulsion for boosting the compartmentalized enzymes. We're working in the development of the different vesicular structures as a delivery vehicle target specific. We're working on development of the nanogels, which has nothing but the small hydrogel particle dispersed in the water, which has a huge influences in the environmental remediations and medicinal chemistry. We also work on the exploitations of the carbon nanotube towards as a cellular transporter by exploiting its hydrophobic surface area. And there's the fantastic another structures, which is intrinsically luminescence, is the carbon dot, which could be derived from the small organic molecule, and that has a huge prospect in theranostic applications. And these fluorescent organic nanoparticles, and which upon aggregation shows the emission, and today I'll be talking about in this domain with a few examples. Now the questions, the fluorescent nanoparticles that are being in sensing applications, and not only sensing, other bioimaging and so on, is there in the literature. So what is new in this fluorescent organic nanoparticle then? Any kind of nanoparticle we are trying to use, or like a semi-quantum dot or organic dye and so on, quite obviously it was generally it is observed that with increasing concentration or upon aggregation, there is a phenomena called the aggregation cost quenching that the emissions of the, quench the emission of these organic dyes. And primarily in most of the cases, it happens the pi-pi interactions leads to the effective quenching because of the non-radiative deactivation pathway. So herein, instead of that, if we can make, and also in this quantum dot or metal nanoparticles, they show some sort of toxicity in the cellular system. So instead of that, if we can design an amphiphilic molecule, which could be weakly luminescent or non-luminescent, but upon aggregations that can be luminescent, which have a better stability, better compatibility, and better acceptability in the physiological system. So to this concept, in 2001, the Tang group bring in the concept of the aggregation of induced, where a normal molecule which are emissive in solutions and non-emissive in aggregate state, this kind of molecules shown are aggregations in the, emission in the aggregate state. And the characteristic feature that was which observed in such molecule is that they have restricted intermolecular rotations, they have charge transfer facilitated by the donor acceptor moiety in that molecule, and they have a generally non-planarity and the chirality in its structures. A few of the examples given over here. So what we plan to make use of, we make use of this kind of simple molecule naphthalene diimide and naphthalimide in our studies because of two reasons: their abundances, and also your synthesis skill need not to be so challenging. You can make it modulations far more easily using this kind of molecule. So herein we'll be using today, showcasing today the FANPs in biosensing. So the first molecule which we have chosen is the protein disulfide isomerase. You all know about this molecule, which has been quite abundant and overexpressed in many of the cancer cells, including melanoma, breast cancer, and so on. And PDI exists in two forms, in the oxidized form as well as in the reduced form. And it involves in the proliferation and survival and metastasis of several cancers, participations through the unfolded protein response. And this molecule in the oxidized form available in the endoplasmic reticulum in the cellular systems, which forms a disulfide bond from thiol. And conversely, the PDI reduced form, which is mostly available in the endosome and cytosol of a cell, and which converts disulfide to a sulfide, and corresponding thiol. So this overexpressed PDI we'd like to determine by designing this fluorescent organic nanoparticle in such a way that will selectively sense the PDI, as well as it can diagnose the cancer cell over the normal cells. So as a result of that, what we have done, we have came up with these two molecules, which is a bit complicated in nature, but after a lot of failure and trial error method, we have come up to this molecule. And you just look at this, it has a disulfide NINSS bond, and it has a thiol bond having a tosyl group connected to the ethylene diamine, which is a ER targeting moiety, this one. And this is a disulfide bond. And it happens to be, we did this corresponding characterization, we found that it shows the self-aggregated organic nanoparticle from the microscopic through the J aggregations, and corresponding fluorescence was observed. And interestingly, upon aggregation, it showed blue emissions for the disulfide molecule in the range of 470 nanometer, and so the bit of orange yellow emissions around 550 nanometer by the thiol moiety. And we did all other spectroscopic, microscopic characterizations. Then we move on to make use of this molecule for the real objective for PDI sensing. So initially what we have done, we have taken this disulfide containing molecule, and this PDI in its reduced form. What happened? It should reduce this disulfide bond and form this thiol one. So it is a fluorescent one, it is a non-fluorescent one. So as a result of that, what we could see a very easily slow decline in the emission intensity with the increasing concentration of the protein in this system. And that was quite obvious. But what happened, you could see there is little sporadic nature in the declination in the emission intensity. There is some hike, a jump. So why is it so? So looking at the mechanism, what we found, this disulfide is getting reduced by this PDI reduced form, and led to the formation of this thiol, and this PDI itself gets converted to its oxidized form. So after a critical concentration, what happened? This PDI and this thiol can get oxidized back to this disulfide by this oxidized PDI. So as a result of that, there is a possibility that this energy, the fluorescence of this disulfide molecule can restore back. As a result of that, there could be a little hike which did not see the complete steady emission. In natural system, what happens? This kind of catalytic cycles get ended by a beautiful electron donor molecule like the glutathione or NADPH or DTT and so on. So whatever happened, we have did the same reactions in the presence of the minute amount of glutathione. So since the glutathione has a better affinity towards this oxidized PDI, so instead of reactions with this thiol, the glutathione will start to react with this PDI oxidized form. As a result, this glutathione will be converted to corresponding GSSSG, and PDI will be restored back to its completely reduced form, which was not possible. So eventually, this reduced form, this oxidized form, no longer react with this thiol, which has been formed from the disulfide. So as a result of that, what will happen? We have seen the complete steady decline in the emission intensity in the presence of the glutathione with a limit of detection of the 12.6 to 17.7 nanogram per ml. So the same thing happened when you have done for this thiol moiety, which sends the PDI in its oxidized form. But interestingly, this thiol is converted to disulfide, and here you could see there is a drop in the emission intensity of the thiol with increasing concentration of the PDI, but there is a beautifully another peak is coming up, having a red emission around 625 nanometer, because the disulfide itself also form another aggregated organic nanoparticle, which also have a red emission. But here with increasing concentration of the PDI in the oxidized form, you could see again that quenching or enhancing in the emission also not straightforward, because of the similar reason that the oxidized, this thiol gets oxidized to disulfide, and this reduced form of PDI will again react with the disulfide and send it back to here. So here what we have done the same reaction in presence of little bit of glutathione disulfide. As a result of that, instead of reacting on this reduced form will react on this glutathione disulfide and lead to the formation of the PDI in its oxidized form. So PDI on its oxidized form goes back by the presence of the glutathione. So there is easily the PDI in its oxidized form can be sensed by this FONP selectively at a range of 11.7 to 16.5 nanogram per ml. Since so in nutshell, it has been done also for the cellular imaging, where we have seen the cellular imaging can be done selectively on the cancer cells over the normal cells. Where the picture is not that so clear, and there is a mean fluorescence intensity of 47 against 189. Similarly, for the oxidized form also can be seen with increasing time and the concentration of the PDI overexpressed in cancer cells. You could see very high rate fluorescence, which has been shown because of this formation of the disulfide, which has a 625 nanometer emission. So we have been able to selectively sense the PDI in its reduced and in the oxidized form by the designing of a different kind of FONP. And I'll give few more examples of the similar oxidoreductase enzyme, which has been overexpressed in the cancer cell, and that also can be sensed by this different aggregated organic nanoparticle. One like the lactate dehydrogenase A, which is overexpressed in cancer cells because it's involved in the glycolysis, and the tyrosinase A, which is also overexpressed in the melanoma cells, which is involved in the oxidation of the polyphenol compounds to the corresponding melanin through the formation of the dopaquinone. So first with the lactate dehydrogenase A, which primarily involved in the glycolysis from pyruvate to lactate formation, because in normal cells, the ATP energy production takes place through the mitochondria and TCA cycle, but in cancer cells, because of the high demand of the energy, they bypass this pathway and they move through this glycolytic pathway. In glycolysis pathway, the pyruvate to lactate formation takes place due to the presence of this overexcess of lactate dehydrogenase A. So we wanted to sense this lactate dehydrogenase A by making the diagnosis of the cancer cells. So what we have done, we also had done a lot of permutation combinations, a lot of failures are there, and eventually come up with this molecule, naphthalimide-based amphiphilic molecule having a aliphatic pyruvate in its arm. And this molecule, because of the naphthyl substitution, also shows a beautiful EOLO emission around 590 nanometer, and it shows corresponding fluorescence. And then we have checked its ability to sense the LDH. So pyruvate to lactate conversions takes place by the presence of this LDH, which is coupled with the conversion of the NADH to NAD+. So when you checked the emissions quenching of this compound FANPs by this enzyme, we have seen there is a decrease in the emission intensity around 590 nanometer. Alongside, there is also decrease in the emission around 420, 425 nanometer, which is the drop in the emission intensity of the NADH. So the question may come then, what is the need of utilizing your FANP for sensing this LDH? Because the NADH itself can do the sensing. But when you follow the sensing mechanism from the Sternberg plot and the corresponding deductions limit has been determined, we could see our FONP has a limit of deduction around 18.6 nanogram, having a very high, very nice linearity, in contrast to the NADH, which is around 100 nanogram per ml, having a very poor linearity. So it is 5.4 higher selectivity, as you could see by this FONP for selective detection of the LDHA. And that has been also observed in the corresponding sensing of the cancer cells. You could see the normal cells has a very high fluorescence of this FONP having a MFI of 1445, whereas the cancer cells got a 459. So quenching has been takes place in the cancer cell of the FONP because of the high presence of the LDHA. And that was further confirmed by using a corresponding inhibitor of the LDHA, which is sodium oxamate, where you could see by the presence of the sodium oxamate, there is a restorations of the emissions around 1016 from 459, which makes it more selective that the LDH has been since the FONP. And that was further confirmed by using another experiment where the normal cell HEK has a lack of LDHA. What we have done, we made a transfections with a construct so that LDHA can overexpress with the GFP tagged, and where we could see there's a lot of green signal, but in contrast, the FONP's emissions got quenched because of the high expressions of the LDHA in the normal cells. As a result, we have been able to make a selective sensing of the cancer cell or diagnosis of cancer cell by using these FONPs. And this work was carried out by Kothakoli, Shomuli, and Debolina. And finally, the last one I would like to share that we also have done the fluorometric sensing of the tyrosinase, where we have used this naphthalimase molecule having a morpholinome attachment for targeting melanosomes, as well as this catechol moiety, which are selective for the tyrosinase enzyme. And it also showed aggregation-induced emission in the green range, having around 520 nanometer and so on. And it also showed emission in quenching in presence of the tyrosinase enzyme, having a limit of reductions of 58 microunit per ml because of this oxidation of this OH group to corresponding dopaquinone and the corresponding melanin, which shows a very selective sensing. And that selective sensing was also observed in case of melanoma cell, in contrast to the other normal cancer cell or normal cells, which has a 1.3 to 3.4 high selectivity. So in summary, I would like to say that we have been able to prepare a different kind of aggregated organic nanoparticle, which has been made to be fluorescent, and that has been selectively utilized for diagnosis of different kind of cancer cells by exploiting their AI-induced fluorescence property, by like making a PDI sensing, tyrosinase sensing, or LDH sensing. So in final, I would like to thank all my students. Prior to that, I would like to thank my mentor teacher, Professor Aurobindo Choudhury, under whom I have did my doctoral studies, and he had made me a nice guidance throughout my research journey as well as my personal journey too. And I'm definitely thankful to all my past scholars who have been instrumental of establishing my laboratory and my research activity at ISCS, and of course my current scholars who have been a constant source of learning in my pathway research journey. And thank you for your kind patience.
Thank you, Prashant. A few questions? If there are.
Yeah.
Yes.
So for this nanoparticle sensing for diagnostics, how many, after the onset of cancer, how long would the progression need to take place before you can actually implement the diagnostics? How many cells do you need? How sensitive is it?
Yes, thank you very much. So, Professor Majumdar, I would like to say that what we are sensing here, we are trying to sense taking a cell culture from the cells, where we are taking around 1,000 kind of number of cells. And that cells are being able to, because we need a critical amount of the enzymes to be present there, after which we will be able to sense that. If our PDI or LDHA concentration is too low, then definitely would not be done. So we need to have at least certain around 500, 700 nanogram to certain microgram ml of enzyme expression is needed, before which we will be able to sense that. So we need a definitely certain level of growth, but I exactly cannot tell you that what exact content, but which grade of cancer will be able to sense it. But yes, we need a certain critical concentration definitely.
Very interesting observations.
Thank you.
How do you propose to use this in a clinical situation?
Yeah.
In vitro or on tissue specimens, once biopsy is available? How does one use this?
Thank you, sir. So first of all, our study so far is limited to this 2D cell culture study, but I tried to done this study in the 3-dimensional tumor spheroid model first of all. But unfortunately, the problem is in the tumor spheroid model, in 2D cell cultures, we'll be able to segregate out the cells from the dye itself. But in 3-dimensional tumor spheroid model, we are not being able to do that. But it is already intact within the systems. So it has to be tested in the tissue directly. Instead of 3-dimensional tumor spheres, we have not done that in the 3-dimensional tumor spheroid in the tissue models, but we need to collaborate for doing these studies with the clinical or the hospital samples.
But the tumor is inside the body.
But we need to take a sample. Yeah, but either like the PET scan when we have done, we put a dye inside the samples to make a scanning. So to bring these materials to that level, it will definitely take a lot more time. But for the first answer, I think the biopsy sample has to be taken out, and on which we should make an attempt to make a sensing over there.
Yeah, we have one last
Sir,
question.
I have one quick question.
Yes.
So how effective this method as compared to the laser-based mechanisms such as optical trapping?
I mean, we have been compared this method with respect to the corresponding different other sensing methods. In most of the instances, it's comparable or better. But what method we are referring to that exactly not comparable to this pathway what we are referring to. So in some of the analytical sensing method, it's sometimes better or sometimes comparable to that actually. It's competitive. I would not say it is the only outstanding method. It is competitive.
Thank you. Thank you, Prashant. All the best.
Thank you very much. Thank you.
Thank him from the academy side. Thank you. Our next speaker is Dr. Ms. Sandhya Shenoy from the Srinivasa University in Mangalore. And she's going to address us on the development innovations of high performance thermoelectric materials. As she's preparing for the mic, she's also a recipient of a number of Young Scientist Award, including Kalpana Chawla Award. Very nice to hear on this subject. The mic is over to you, Sandhya.
Good morning, everyone. At the outset, I would like to thank the Academy for providing me an opportunity to deliver this talk. Today, I'll be presenting on electronic structure engineering for the development of high-performance thermoelectric materials. Thermoelectric materials are the materials which have the ability to convert temperature difference into electric potential. There are two kinds of thermoelectric devices. One is thermoelectric generator and the other one is thermoelectric cooler or Peltier cooler. So this is a schematic representation of a thermoelectric module wherein the P and N type legs are connected electrically in series but thermally in parallel. In case of thermoelectric generators, the temperature difference applied across the P and N type materials generates electric voltage because of the diffusive flow of charge carriers, while in the case of thermoelectric coolers, voltage applied brings about temperature difference. So world's demand for energy is primarily met by combustion of fossil fuels. This has an adverse effect in the form of global warming, and also about 60 to 70% of energy utilized is wasted in the form of heat. Now, if this heat could be scavenged, then that would be great. So this is where the thermoelectric materials come into picture. So although all the materials have got non-zero thermoelectric effect, but in most of the materials it is too small to be useful. And despite low efficiency of thermoelectric materials, they are used in a variety of applications, basically because of their reliability. Thermoelectric devices have the advantage of being they are kind of stable. They are solid state devices. They do not have any moving part, okay? And because of this, they can be used in harsh environments for extended periods of time without human intervention because they are maintenance free. So now, why is this work challenging? The effectiveness of a thermoelectric material is given by the dimensionless figure of Merritt, and the efficiency is given by this equation. Here, alpha is the Seebeck coefficient, sigma is the electrical conductivity, and kappa is the thermal conductivity. So this factor is called as the power factor. So in order to have high figure of Merritt, we need to have high power factor and low thermal conductivity. So now if you see here, Seebeck coefficient is inversely proportional to carrier concentration, whereas electrical conductivity is directly proportional to the carrier concentration. So hence, if we increase the carrier concentration, the Seebeck coefficient decreases and the electrical conductivity increases. Now, since electrical conductivity is linked to thermal conductivity, that is the electronic component of thermal conductivity, the thermal part gets tied up to the electronic part. I said thermal conductivity has to be lower, and there are two sources of thermal conductivity. One is the electronic thermal conductivity, which is because of the electrons and holes carrying the heat, and the other one is lattice thermal conductivity, which is because of phonons traveling via lattice. So how should a material be? The material should be high in electrical conductivity, that is like a metal, and it should induce high voltage in response to a temperature difference like a semiconductor, and it should be a poor heat conductor like glass. So now how do we design a high performance thermoelectric material? Okay, lead telluride is one of the most well-known thermoelectric material, but because of the toxicity of lead, its usage is not advisable. Tin telluride, on the other hand, is its rock salt analog, and it has similar electronic structure. But tin telluride is a very poor thermoelectric material, okay, because of its intrinsic vacancies, which increase the carrier concentration, and also it has high thermal conductivity. And also, if we look at the electronic structure, we see that tin telluride has smaller band gap in comparison to that of lead telluride, and the energy offset is higher, which means these bands do not participate in the transport. So what are the strategies to improve the power factor? As I said, carrier concentration is one of the important parameter. It could be tuned either by self-compensation or by donor doping. And power factor can also be improved by band structure engineering. So if we see here, we see that when the temperature increases, the band gap increases, but yet it is not sufficient enough to prevent the bipolar diffusion, which is detrimental to ZT. So therefore, if we can add a dopant such that the band gap increases and the valence band offset decreases, then it would be promising. The Seebeck coefficient of a material is directly proportional to density of state effective mass, which is given by this equation. Here NV is the number of degenerate valleys and MB star is band effective mass. So in case of tin telluride, we have valence band, that is light hole valence band at L point with NV of 4, and we have heavy hole valence band at sigma point with NV of 12. So when we converge these two, then we'll have increased NV. So increase in NV can be visualized as increasing number of lanes on the road, so that it will facilitate smooth traffic. So increased NV here means there is more number of conduction pathways for the charge carriers to take part in the transport. Also, another way of improving the power factor is by introducing resonance level. Resonance level arises because of the coupling of electrons of the dilute impurity with that of the conduction or valence band electrons. This increases the density of state near the resonant energy. If the Fermi level can be brought close to this, then we'll have increased MB star and in turn Seebeck coefficient. And here, as we tune the electronic structure, the dopant what we have added will also reduce the lattice thermal conductivity because of scattering of phonons of short mean free path. Lattice thermal conductivity is the only parameter which is independent of carrier concentration, and it can be decreased either by atomic scale, nanoscale structuring, mesoscale structuring, or employing all of these together in all-scale hierarchical architecture. Now what happens is, when we introduce a nanoparticle within a bulk material, there may be generation of additional energy barriers, either because of the crystallographic mismatch or the band misalignment, and because of this there will be scattering of the charge carriers and it decreases the mobility of the charge, and hence we need to decouple the electron and phonon transport, and it can be done either by strained endotaxial nanostructuring, matrix precipitate band alignment, or by compositionally alloyed nanostructures. So now let us see how electronic structure engineering can be used to improve the performance of tin telluride. Magnesium and calcium were known to increase the band gap of the tin telluride and also cause valence band conversion, and indium was the only known resonant dopant till 2019. So when we co-dope this, we see that the dopants play different but complementary role. Indium increases the performance at lower temperature, while the other two dopants increase the performance at high temperature. In the case of magnesium indium co-doping, we achieved a ZT, that is the figure of merit, of 1.5 at 840 Kelvin. In case of calcium and indium co-doping, since calcium had higher solubility, we maintained 2:1 ratio and we achieved a ZT of 1.6 at 840 Kelvin. And this material exhibits the highest power factor achieved by far in SNT based material. So now, the previous technique wherein you co-dope two different dopants, though they increase the performance at higher temperature, the performance at lower temperature was mediocre. So there was necessity to find some other approach to improve the performance at low temperature. So bismuth, which was basically used to tune the carrier concentration of tin telluride, we studied its electronic structure and we saw that the p orbitals of bismuth hybridized with the p orbitals of the host, giving rise to what you call resonance level. So for the first time we tried co-doping a p-type and an n-type resonant dopant, and we see that while we increase the concentration of bismuth, the band gap increases and the band offset decreases. So in this case we achieved a ZT of 0.25 at 300 Kelvin, and at 840 Kelvin it was 1.32. So I said indium is a very good resonant dopant, but the problem with indium was when you increase the concentration of indium, the electrical conductivity drastically decreases, and hence we were trying to find some other kind of resonant dopants. So the electronic structure of zinc doped SNT showed promising features. Here we see that the zinc s orbitals hybridized with the tellurium p orbitals, giving rise to resonance level. And because of the increased density of state and increased effective mass, we see that the Seebeck coefficient drastically increases at room temperature, and this material exhibited a ZT of 1.28 at 300 Kelvin and 1.49 at 840 Kelvin. So in order to further improve its figure of merit, we co-doped it with the bismuth, and in this case the bismuth p orbitals, zinc s orbitals hybridized with the host p orbitals, giving rise to resonance level which almost mirror each other. This unique electronic structure led to a record high room temperature ZT of 0.3 in lead-free SNT based material and a peak ZT of 1.6. So we can see that zinc doping helps a lot in improving the thermoelectric properties of tin telluride, but it has a disadvantage that the lattice thermal conductivity exhibited is high. So now when we alloy lead with SNT, we see that the thermal conductivity drastically decreases. But the problem here is that the band gap also closes, which will lead to bipolar diffusion. So when we dope zinc into it, we see that the band gap increases, there is introduction of resonance level, and in addition to this, there is phenomenon of hyperconvergence. That is, the heavy hole valence band increases in energy compared to that of light hole valence band, and this increases the Seebeck at room temperature, leading to a ZT of 0.35 and a peak ZT of 1.66, and this material exhibited an average ZT between 300 and 840 of 0.9, which is actually a record high value. And when instead of zinc, when we doped bismuth, we predicted a ZT of 1.58 at 800 Kelvin. So in order to make the material lead free, that is non-toxic, we alloyed germanium, and even in this case we see that the band gap decreases, and hence we dope zinc, which again here led to increase in the band gap, introduction of resonance level, and in this case we see that the bands, that is the light hole and heavy hole valence band, are perfectly converged. zinc was also co-doped with other elements, and when the ratio was maintained similar for all the three cases, we saw that the lead-free silver-zinc combination showed maximum ZT of 1.54. So as I said in the beginning, for a thermoelectric material, we need both P and N type legs. So when we studied the electronic structure of tungsten doped SNT, we saw that tungsten increases the band gap, it causes convergence of the valence band. In addition, it introduces multiple electronic valleys near the Fermi level, and the unique feature was hyperconvergence of conduction band. This was reported for the very first time in the case of tin telluride, and this feature was not seen in molybdenum or vanadium doped cases, and also the tungsten d orbitals increase the density of state near the Fermi level, and hence we predicted a ZT of 1.61 in this case. And since it showed promising features for both development of N and P type materials, so more studies need to be conducted on this material. So I would like to take this opportunity to thank Professor K.S. Narayan sir for nominating me for the associateship. I am also immensely grateful to Professor Krishnabhat sir, who is my collaborator and who has been an immense support throughout my research activities. I thank all the co-authors of my papers. I acknowledge the funding from DST under Inspire Faculty Fellow Scheme, Science and Engineering Research Board under SRS and EMR scheme, and CSIR under EMR scheme. Thank you, one and all.
Thank you, Sandhya. A few questions. A little bit time. Yeah, there we are.
Very nice talk.
Thank you, sir.
Yeah. The temperature dependence of the band gap.
Yes, sir.
Is it because of the impurities, or for pure substance also?
For pure substances, sir. For pure substance itself, we see that when you increase the temperature, the band gap will open up, but it is not sufficient at high temperature to prevent bipolar diffusion, sir. Because in case of tin telluride, if we see, for about 800 Kelvin, in order to stop the bipolar diffusion, we need a band gap of around 0.4. So in case of SNT at room temperature, the band gap is 0.18. So if we consider the temperature effect, that is the band gap opens something around 4 into 10 power minus 4 EV per Kelvin. So it will be around 0.38. So still it is not sufficient. It does not reach 0.4. So there will be bipolar diffusion.
So you've done the calculation, finite temperature calculation?
No, sir. That is a well-known thing. Like the amount of band gap required for a particular temperature, that is already established. What we do is we just check the conductivity values. Like what happens is Seebeck and as well as thermal conductivity values. If at all there's bipolar diffusion, there'll be an upturn. Or in case of Seebeck, there'll be a downturn. So based on that, we'll know whether there is bipolar diffusion occurring or not.
Okay. So you use the Fermi-Dirac distribution for the calculation?
We don't actually calculate what is the amount of bipolar diffusion. We just check the Seebeck coefficient, if it is increasing or decreasing.
Yeah. So when the thermal conductivity decreases when you introduce lead, is that mainly the phonon thermal conductivity going down, or is it also the electronic contribution which goes down?
It's actually the phonon ones. Like the maximum thing is phonon because of the weight difference.
Right. So the electronic thermal conductivity is not changing very much. You're saying it's the phonon which is.
Yeah. So that's why we add actually zinc. So because it also distorts the electronic structure. So to compensate for that, we add zinc so that the band gap opens.
I see. Okay. Yeah. Thank you.
Excellent science.
Thank you, sir.
How do you prepare the material, particularly the one with the tungsten? There are high melting materials.
It's seal tube reactions. Like we take the starting materials, we add it into a quartz tube and then heat it to a very high temperature and a vacuum.
By what? Induction melting, arc melting, or what is it?
No, sir. For some of the things, it's normal melting. Like in the oven, we reach up to 1200 Kelvin or so. And also in some cases like SHS and all, we directly use a flame torch to heat the samples.
No, tungsten being high melting.
Tungsten, we haven't synthesized it yet, sir. We have just calculated the electronic structure yet to synthesize.
Okay, thank you.
Well, if, yes, there we are.
I was just wondering, the substitution by bismuth seems to have distorted the lattice. So if you were to take antimony, it might be less of a distortion, and yet you might have similar effect. Is that possible?
Pardon, sir?
You had a doping with bismuth.
Yes, sir.
If that seems to distort the lattice to some extent.
Yes, sir.
Now, if you use instead of bismuth antimony, probably it may not change, because the tin and antimony are not really so far apart in terms of size. So I was just wondering, you have tried this?
Antimony, it's already tried, sir. They have, basically they use antimony to change the carrier concentration, and then they add some other dopant to have impact on the electronic structure.
Okay. Thank you.
Thank you. And if there are no more questions, we thank Sandhya Shenoy for the wonderful talk. Thank you very much. And now we invite Jagdish. Our third speaker, please come, take this. Wonderful. He's going to shock us with shocking waves and healing touch. It's very interesting. And he's a chair of the Department of Aerospace Engineering and founder chairman of the Center of Excellence in Hypersonics at IISc Bangalore here. And his topic on shocking waves and healing touch is going to be very interesting for all of us with that healing touch. Jagdish, the chair, the time is yours.
Lovely good afternoon, ladies and gentlemen. It's such an honor to speak about this in this particular hall especially. So what I have done is probably the work of hundreds of students and maybe tens of collaborators, and it is all because of them that we ended up doing something of this kind. Yeah, sorry about it. Of course, the word shock is quite interesting. For some people, when you go and look at the notice board after an examination, you do get a shock. But I am not referring to that shock here. And as youngsters, you put your finger in an electric socket, although parents would say, don't do it, you may get a shock. I am not referring to that. And it is also not the thermal shock that biologists usually talk about. So it's purely a mechanical phenomena where there's a sudden equation of change that happens whenever these kind of waves propagate through a medium. But then the shock wave itself is a misnomer, because there is no wave number or a real classical wavelength that you associate with sound waves. But because it emerged from the analogy of classical acoustic principles, the word shock wave has stuck to it. Just before I get into that, a big thanks to colleagues in the department, especially Professor Deepshika, Professor Satyam, Professor Arunan, who are also fellows of this academy, for a wonderful journey that we have had. And we realized that although you work in silos in different departments, if you start collaborating and talking to each other, probably we can walk far in the entire journey of pursuit of the unknown. Before I go, I thought in this audience, it is also good to remember the founding fathers of this great institution, Indian Institute of Science. While everybody thinks about Mysore Maharaja and everybody talks about Swami Vivekananda's role, seldom do you hear about this great lady, Kemparajamani Vanivilas Sannidhana, who was the mother of Nalvadi Krishnaraja Odayar when the actual land transfer to IISc took place in 1908. This noble lady was a phenomenal queen. In fact, when she wanted to institute a scholarship for poor children in Indian Institute of Science, the first British director, Maurice Travers, on record, refuses to institute. Still, the Mysore kingdom was giving 50,000 rupees to this institution till 1947. So it's an amazing story of how a noble queen who never stepped into this particular institute was able to play a big role in the formation of this IISc. Science is always, nowadays, I feel very offended whenever people say in research boards, what is the use of this research? What is the outcome? Will there be a technology? Will there be something that comes out? Because I always believed unheralded, curiosity-driven pursuit of the outer nature is science. Asking question, why is actually science? Probably that is the reason why, according to the Hindu mythology, the Brahmadeva was supposed to be the creator. and you hardly have any temples for Brahma in India also. So nobody likes science because you can't see science. So, but it is important for know why before you really look at why not as engineering. Engineering, of course, we are more like Narayana, where not just Dashavatara, but we have Swiggy, Zomato, all kinds of avatar, because we ask the question, why not? Technology, of course, is more like Shiva, because the day it is born, it is actually destroyed. And thanks to this entire word of shockwave, in our own campus, we were able to go through this entire journey of asking the question why, asking the question why not, and finally building a product which is actually reaching out to common man. Of course, shockwave now we have seen, we never thought that we will be able to touch upon several disciplines when we began work 3 decades back. But today there are students from material science department, biology, chemistry, physics, as well as instrumentation, all use the facilities which was set up in the department. Just one quick word on shock waves, what it is, because while I am speaking, sound waves are traveling. Of course, there is an amplifier here, but when sound waves travel through a medium, it does not alter the temperature and pressure of the medium. Usually it is isentropic. But if that were to be a shock, if I start shouting, screeching, then the rate at which the energy is being deposited, the molecules which actually vibrate in air, obviously they are going to be beyond 10 to the power of 14 hertz. And then suddenly you start accumulating of local waves, and that compression waves, when they start accumulating, suddenly you have a wavefront across which properties change very drastically. Welcome to the world of shock waves. Shock wave is a phenomena. Suppose if there to be a shock that travels here, touch wood, it should not happen, but then if there is a bomb blast, you will have a shock which would propagate at supersonic speed. Suddenly you will not even realize that it has passed through you. You will find that your entire body would be squeezed in and squeezed out. In fact, interestingly, we did a study with NIMHANS. The cracker burst, there is one particular variety of cracker which makes very loud noise, and we exposed some mice which were typical of the brain of 6 years to 12 years. To our dismay, we found 3 such exposure is good enough to bring down the cognitive abilities 30%. In fact, we did work with the government asking them to reduce the decibel levels. Trauma-induced brain injury is a major problem that you really experience in the battlefield. With all your protective gear, the blood flow in the artery actually shrinks by close to 30% just because the soldiers are exposed to these kind of loud shock waves. I would say loud because you can't even hear the sound. Once you hear the sound, then it is no longer shock. In fact, for aerospace people, why this is important is whenever a vehicle travels at, say, supersonic speed, you will find these beautiful shock waves. Of course, they all look very beautiful, but for me, I need to know what is the distance between that wave and the body, the so-called thermal protection system, which is so vital. Kalpana Chawla's accident is one stark actual example. When the space shuttle re-entered the Earth's atmosphere at velocities of about 22,000 kilometers per hour, which is an enormous velocity, and it came across a stationary Earth's atmosphere, then they were virtually burnt alive because during the ascent stage, they had a ceramic brick which had loosened up. And because the local temperature during re-entry became something like 440 degrees centigrade inside the space shuttle. So for us, it's a natural hazard. Every day we need to find out how these waves are actually behaving. But of course, if you look at nature, you find plenty of such examples, including the shock waves which come out of the large stars when they explode in the outer space. In fact, there's a wonderful group in TIFR who work on relativistic shock wave, and the shock waves there in outer space, they travel at about 50 kilometers per second. Knowing the dimension or the radii of the shock wave, we can actually go back and estimate what is the energy that created this. The classical Oppenheimer's example during the atomic bomb was they measured the particle velocity and they were able to estimate what kind of payloads were used. Even in the Pokhran blast, when you measure the pressure at a far distance, you can actually work back what is the energy. So it's all over the place. But again, very curiously, of course, circus it is now. I don't know how many of you have visited circus. The hunter or the master who has a whip and then you do it, actually there's a tiny shock wave which is generated. By law, hunter is not going to, trainer is not going to be allowed to hit the animal. But then the very fact that he does this, the shock can go through you, and even 0.6 bar of pressure rise that happens is good enough to rupture your lungs. So it's almost like an electric shock. Of course, there is a component of infrasonic in many of these, because even in a zoo, whenever the tiger roars, you usually feel as if it's a goosebump moment. That is because your body's natural frequency is about 18 hertz, typically 18 to 27 hertz. So it's a very interesting phenomenon. But surprisingly, that if you go deep below the sea, there are what are called as pistol shrimp. And when they move their claw, there is a cavitation bubble which actually ruptures, creating a shock. And whenever these are moving around, submariners usually mistake them as pistol shrimp because the amount of sound they make is as good as the sound made by somebody is actually blasting something underwater. So it's a very interesting phenomena which exists all over us, and it's not something very new. But just few slides on what really is happening to future conflict. I'm sure that all of you are aware of the kind of conflicts that are happening at all over the place in current scenario. And we increasingly see that the knowledge and resources and information appears to be the driver in the way the whole world is moving. And in this, hypersonics is actually the buzzword that you're hearing everywhere. Today, people are looking at hypersonic transport where you could travel anywhere in the world in 1.5 hours. There are private companies in Germany who are looking at cargo transfer using hypersonics, so that they are looking at something which is revolutionary. Supersonic aircrafts have also again come back in big time. Both Japan recently did a 14-seater flight trials using supersonic aircraft. Concorde was shelved, but now I think it is coming back in a different way. People are looking at all kinds of crazy things, including missiles. In fact, the Chinese moved around 43,000 kilometers in 2024, and the vehicle was in actual flight for more than 100+ minutes. It's a hypersonic glide vehicle. Nobody could detect that. And first time publicly they acknowledged, and today there are massive programs across the world on hypersonics. This is a view of our own lab, which we started in a modest way, thanks to generous help from Dr. Kalam and several people. Today, this is one of the largest labs in the area of shock waves in the entire world in a university. All these facilities are indigenously developed by students and faculty members from several departments. We can recreate hypersonic flow in the lab. And in fact, I still remember when Dr. Kalam came several years back, he was saying, show me a shock wave in the lab. I would believe that you can do such experiments in 1 millisecond runtime, because that's the typical experimental time. But thanks to the high-speed cameras today, we can actually see what is happening within 1 millisecond in the lab. Even the entire re-entry flow that we really talk can actually be recreated in the lab. And there are only 7 countries in the world who are capable of doing this. Thanks to the efforts of several people, I think IASC also is in the bandwagon. The Center of Excellence does several things. I won't get into the detail. This is entirely a multidisciplinary approach where you need high temperature materials, you need novel guidance system, good insight of chemistry. People think basic science will not be able to do something. Without basic science, no technology can emerge anywhere in the world. So just how much we strengthen the basic science, maybe country can actually look at some progress. These are several areas. I will not get into details except to tell you that we are involved in looking and understanding shock waves throughout our life, including the so-called scramjet engine. This one, which you can really see, where supersonic jet engine, this is an engine without any rotating parts, and people are trying to build this engine across the world, including China, America. China already has a scramjet engine. If you have such an engine, you can actually have an engine where the temperature and pressure behind the shock is used in combustion. So it's a very interesting kind of a phenomena. Of course, there are several facilities where you can really do these things, and a lot of data, including the hypersonic flow transition, becomes very important. The novel new type of engines that we develop, they need special, materials, special kind of structure. It's becoming more like a problem of system engineering. Of course, in the chemistry part, which I mentioned, one of the chemical kinetics and dynamics associated with combustion phenomena in short duration is the most critical part when you can build an engine. This is a clear demonstration that if you don't understand chemistry, you cannot build a technology. So it's very important for us to strengthen basic sciences as much as possible in the laboratory. Of course, there's a grand vision that India has to become quite self-sufficient in this. Even texture modification in a conventional material science, with what we did with Professor Satyam, is very revealing. Shockwaves are also able to modify the texture in classical materials, leading to some very interesting fundamental phenomena. One of my students ended up writing a nice tree. In fact, today we have used shockwaves for all kinds of bizarre things, including how do you make your tea taste better. And if the tea leaves are exposed to shockwave, more polyphenol comes to the surface, and actually you can enjoy the good cup of tea. I won't get into too many applications except to tell you that you can actually do a needleless injection using shockwave. This is one of the work that we did with Professor Deepshika. So you have a miniature system and you can actually target the Langerhans cells which are below your dermis, so that the amount of antibodies that you actually put will be much lower than a conventional needle. So there are some exciting biofilm disruption that we can do. So varieties of things, but I'll only say a few things about the whole game. IISc is a wonderful place. The time when I met Deepshika was in some committees in which we are always put, whether we like it or not, but over a cup of coffee, you have biology next door. And if you're willing to learn, I think a lot of interesting things can come out of applications. And one of the very crazy experiments which I just wanted to show you here was, if you expose E. coli bacteria to these shock waves, normally you believe E. coli is few microns, how will it withstand this? I was actually perplexed from a mechanics perspective. But if you have a shock pulse of something like 100 bar for about, say, 30 microseconds, the impulse embedded in that shock, these E. coli are actually expanding and they come back to their original position. I never thought sometime in my life I will end up building or measuring the Young's modulus in E. coli using shock wave. And these are all some crazy experiments which actually happened only because we always believed in enjoying our science, asking the questions purely based on curiosity. And we ended up putting a small mice in a shock tunnel. And what is used for aerospace, we ended up doing it on animals to come out with some very interesting applications. I'll skip the details for the brevity of time, but it is very interesting that certain dosage of shock actually improves your immune protection systems. So these are very early days, but we are toying with the idea, one day when you go to a doctor's clinic, without your knowledge, there would be a tiny dose of shock, and the biofilm basically disrupts. We have seen it in mice that the biofilm disruption by whole body shock exposure gives some phenomenal results. So these are something in some sense actually looking at positive effect of shock. But this is one last slide where I would like to just narrate this interesting success story. Now, this device that you see here, we never thought we would build this device in 2016 when one of our own former student, Professor Sandeepa, he is also, I think, a faculty in the biochemistry here. He came one day and said, sir, what will happen if you expose epithelial cell to shock wave? I said, I have no idea about epithelial cell. I have some idea about shock. So this conversation, which actually started in this manner, eventually resulted in we built up a miniature system where we found that if you expose epithelial cell to shock, then new angiogenesis is forming. Eventually, it led into a lot of interaction, and finally we said, can we heal diabetic wound? Finally, now we have a device which is in a commercial scale. I'm quite happy to say more than 75 patients have been treated, and very worst kind of gangrene, we are able to treat them, provided they are still in the wet form. And we believe, I never thought that we will actually touch common man using shock waves which were actually generated in aerospace. In fact, my own manager in the office got his one toe was amputated, and similar gangrene had started in the other feet. Thanks to this machine, we were able to save. And every day when I see him, he's so happy about it. I think ultimately science will get its due, provided it reaches the society in some form. But then all of us need not do the mad rush to reach the society. Unless there is a big foundation on curiosity-driven science where you don't talk about return on investment, I don't think no country can become a knowledge economy. And this is one of the nice success stories, but we have also built an artificial liver. Again, I never thought we would collaborate with a liver surgeon and look at something for the cure of acute liver failure. And luckily, 5 patients while I am talking have been very happily, successfully treated with this for acute chronic liver failure. Again, knowledge has no boundaries. Engineering, medicine, science, all of them ultimately lead to knowledge production. Cognitive abilities of human being, his ultimate goal in our life is to serve the society, to make a mark and a difference in somebody's life. Thank you, sir, very much for the opportunity. I will stop.
Thank you. Thank you, Jagdish. It's a wonderful talk. I'm sure there are more questions and I will have more problems to control. So, anybody? Yeah. Go ahead.
Tsunami also shockwave. Absolutely. I'm glad that you raised that question. In fact, the tiny version of that is what we observe. Of course, we don't make this observation every day when we brush our teeth. When you open the tap and when the jet of water falls on a flat sink, you actually see a small region where there is absolutely no water and there is a small hump. This is the classical shallow water hydraulic lift. When tsunami happens, the earthquake or earth opens up like this. Usually when they close on the same plane, the amount of water that gets in is much lower and the energy is much lower. Then if the plates start moving like this at typical velocities of about 10 meters per second, that is when actually the impact of tsunami would be very large. And it is, yes, it's a water wave, of course, but then the actual energy is pretty rapid in terms of the deposition. In air, you usually talk about hundreds of meters, but in water, 1 meter per second is a huge velocity that we encounter, whereas the wave that comes out of these movements can travel at almost like 400, 500 meters per second. It's very enormously large velocity.
Yeah, there's one.
So, like in the very beginning of your presentation, you just said that if we somehow came in contact with the shock wave, there would be adverse effect on us. But at the same time, we are trying to research on the micro injection of the shock waves onto the human body in order to cure certain diseases. So, don't you think that's also going to cause some kind of adverse effect on us? Obviously, there will be like some negative effect as well.
It's an interesting question. See, for creation of the shock, you need certain energy deposition. And that energy needs to be released very rapidly in the time scale of few microseconds. As long as you know how much energy you are using and what is the time scale in which you are releasing it, what is the area under the pressure to time curve or the impulse that you generate out of that, you can make it extremely local. For example, in the diabetic wound healing, when I generate a shock in water and use a diaphragm to transfer it onto the skin, my area of zone of influence is only 5 millimeter. Not only I know what is the area of impact, I also know the depth. So once you know all of this, certainly you can do. Otherwise, it can be very catastrophic. In fact, the extracorporeal lithotripsy that they use to destroy kidney stones, many of them have reported secondary and tertiary damages because if you move a little bit, obviously it can create havoc because the peak pressure there would be of the order of about 40 MPa. But then the duration is very small. So it's very important in these kind of application to ensure the right kind of peak pressure and the right kind of time duration. The biology bacterial experiment which I told you, if you increase the duration to say something like 60 microseconds, bacteria dies. But then if you can keep it to somewhere around 30 microseconds, they can withstand 110 bar above the atmosphere, which is again mind-boggling. But then again, it is very important for us to control both the energy as well as the time scale.
So it's all the matter of precision.
Absolutely.
So just one more question, like what are the diseases that we are trying to, cure using this method? If I meant to know.
We cannot cure any diseases here. The only thing that we are doing in wound healing is because it destroys biofilm and produces angiogenesis, we can avoid amputation in diabetic patient. Of course, diabetic wound is a much more complicated thing physiologically. Any open wound that happens after surgery or fall, you can actually, if you expose them to shock, we are seeing that they are healing much faster because more blood flow in that zone. But then we are just beginning some work on looking at how tumors which are cancerous could also be destroyed. With the Chitra Tirunal, we have had some work on how they can destroy by making an endoscopic shockwave generator. Certain kind of during surgeries, they are not able to cut open, but local application of shock is able to shatter the tissue and then they're able to go their way. So, but we are not trying to solve any disease at this point in time.
One last question.
What is the result of your experiments on E. coli and other bacteria? You showed a picture, but what did you actually learn from all that?
It's very interesting. Actually, we did a couple of things with E. coli. E. coli we used as a mechanism to, we have done gene transformation where we were able to put a desired DNA inside as an alternative to your classical electroporation. So that was the reason why we started picking up E. coli, because it does not have subcellular structure. What we are seeing is it is opening up the pore and it is closing, and then it is getting elongated once we apply, and then later on it is coming back to its own original position. So E. coli was basically used as a template. And then we also wanted to see whether you infect certain animals with E. coli and before and after the exposure of the shock and see how it actually manifests. But one of the dreams that we still have is we want to see whether the pore basically opens up and closes dynamically. For that, we may need a miniature device where you're looking at the microscope and really see, because these are all images where we froze it and then took it later. I do not have direct evidence to say that when it elongates, pores basically open. It is purely a hypothesis at this point in time.
This, they're preparing for the next speaker. One young lady wants.
I have a question. So, like you have said, like it can like this shock therapy. It's still a new topic for us, so especially in biological fields. So, if we look into microbiology, there's like antimicrobial resistance that's going around right now. So, there are many strains of bacteria that have become resistant to the existing drugs. So, do you think we can engineer a mini shock, maybe let's say, to break down the a resistant bacterial membrane or something, so the old drugs can act on them again?
Welcome to the world of shockwaves.
Thank you. We should give a big hand for Jagdish for wonderfully taking us through the subject without a shock. Our next, last but not the least speaker is Professor Yogesh Joshiji from IIT Kanpur. Joshiji is a professor at the IIT, and he also has excelled himself in liquid properties. And today he's going to tell us the secrets of thixotropy.
Yes, thank you. Thank you so much, Mr. Chairman, and thank you so much for inviting me to give this talk. We're going to talk about thixotropy. I'm sure more than 90% of people don't know what thixotropy is, so why not? But I must tell you that thixotropy is pretty much everywhere that you see. I'm going to prove it to you soon. So before that, over past more than 2 decades now, I'm at IIT Kanpur. Various funding agencies have supported me, so I must acknowledge them. Students, everything that we all are, of course, are because of students and teachers. So I must also thank the students and teachers also. So with this, let us begin the talk. So before talking about what thixotropy is, let's venture into a familiar territory. Okay, and familiar territory is yield stress fluids. Even more familiar territory is toothpastes that we pretty much all of us use every morning. And after supersonic rockets, this is the experiment that we are going to do of squeezing paste out of toothpaste. If this works, you can see, well, you can imagine, but this should work, right? It's working now? Okay, cool. But, well, paste has already come out. So you take a toothpaste in the morning, open its lid and put it upside down, and you see that nothing falls off. Oh, it's not playing. Okay. So you get it, it doesn't come out, but you need to squeeze it sufficiently hard in order to make that paste come out. And why is it? Because a certain minimum amount of stress needs to be overcome in order to get toothpaste out. And it's just not toothpaste, but variety of materials that we use in day-to-day life, adhesives, creams, lotions, various kinds of food stuff, they follow this kind of property. All right. This was identified as a separate material class by, E.C. Bingham, and I'm sure most of you must have heard this particular name. And more than now 100 years back, he published this very seminal paper. And essentially the origin of concept of yield stress is due to E.C. Bingham. And what he did is that he literally took mud. He took, of course, much more carefully crafted mud. He took clay, water, and of course we know that clay and water makes something like a plastic mud. And Bingham observed that that plastic mud won't flow by itself. You need to, in order to deform that plastic mud, you must overcome a certain minimum stress. He actually passed it through capillaries, so he needed some minimum pressure to be overcome. All right. And then what he did is that he separated viscous deformation from plastic deformation and qualified plastic deformation, that it requires finite friction to be overcome. So this essentially is Bingham, and therefore this particular type of materials are known as Bingham fluids, Bingham plastic. Okay, and all of us must have heard about this particular name. Mathematically speaking, we'll go to mathematics in a moment, but if you plot shear stress on vertical axis and shear rate on horizontal axis, then typically a Newtonian fluid behaves in this fashion. So Newtonian fluid behaves in this fashion, all right. However, for Bingham type of material, the yield stress materials that we talk about, a certain minimum stress needs to be overcome in order to induce flow in this particular material, all right. And this is represented very straightforward way. So viscosity is infinity until that stress is overcome, and then viscosity becomes finite after that stress has crossed, all right, and the material starts flowing. Around 100 years back, Herschel Berkeley proposed another variant of this particular model, wherein Bingham fluid or Bingham model, which shows weakly shear thinning after yielding. Herschel Berkeley proposed strongly shear thinning system, where they added this mu, where if mu is constant, then you have Bingham. If this m and n are of course not constant, then you have actually this Herschel Berkeley fluid. And it turns out that all these toothpastes and various kinds of yield stress fluids that we come across in day-to-day life are beautifully modeled by this Herschel Berkeley fluid. All right. So far so good. So we are talking about yield stress fluids, which we see in our day-to-day life. More so we see them in industrial life. All right. So this is yield stress. Now let's come to thixotropy. Thixotropy was, the term thixotropy was introduced in 1938 by this German person whose name is difficult to pronounce, Fridolin Delitzsch. But the origin of the concept was given by Peter Fee in 1927. It essentially has two components. It's a Greek word, thixis and trepo. It's a material that changes upon shaking. Okay, that is what actually it means, which means that you have a soft solid like material, you shake it and it becomes fluid. You keep it for a while, it again becomes solid. This is thixotropy. Okay, and it's a very fascinating, the classes of material that you see are very fascinating. And what we are going to do is that in this particular small lecture, I'm going to take you through variety of different shades where thixotropy manifests. Okay, all the experiments pretty much are done in my lab. All right. So thixotropy is continuous decrease in apparent viscosity with time, under shear, under shaking, viscosity decreases, it becomes fluid, and subsequent recovery of viscosity when flow is discontinued. When you keep it still, it recovers and you get back the soft solid. All right. Let's see in a mechanistic way what may be happening over here. That material that demonstrates structural buildup. So what happens is that, let's say material is in fluid state and you keep it under constant condition, a structure buildup occurs. So all these units that you can see over here, they undergo some kind of a physical association as a function of time, and structure builds. Structure means it has capacity to store energy. Capacity to store energy means the structure is becoming more and more elastic. So you essentially go from liquid to a soft solid like a behavior. You apply shear, you shake it, the structure essentially breaks down and you get the liquid back. All right. So this is essentially the mechanistic picture associated with thixotropy. And let's see an example wherein we use this aqueous dispersion of laponite. Laponite is a 30 nanometer disc-like clay particle. It's a synthetic clay. You can do it with natural clays also. And this particular clay has negative face. It has positive edge. Okay, means the face has negative charges. Edge has positive charges. And when you disperse it in water, it forms this beautiful house of cards structure. All right. Now we are talking about 3.58% roughly laponite dispersion. Laponite has density of about 2.6, specific gravity of about 2.6. All right. So if you're talking about 3.5, then roughly you're talking about little above 1 volume percent of its concentration. All right. So let's see what happens now. So what we are going to do is, we have taken this, okay, in this video we have taken 3 weight percent of laponite. I'm going to add this in this particular beaker. We are stirring it. After stirring, because of this white powder of laponite has been added, the mixture becomes hazy. As a function of time, that haze disappears and mixture becomes so clear that if I have kept laponite dispersion in one beaker and pure water in another beaker, you will not be able to make out the difference. All right. You remove the stirrer, pour that particular material which is still in liquid state in a vial, and after a while, it has more than 98 volume% of water. It supports its weight. All right, so those tiny clay particles have essentially beautifully spanned the whole space, and it has essentially, it supports its weight. This particular system and various systems like this are used in pretty much all the household and personal care items that we use. All right, if you're using lotion, if you're using any pharmaceutical cream, may not be Laponite, but some or other type of clay or these agents which are thixotropy controls. If you talk to somebody in, let's say, Unilever or Procter & Gamble or ITC or L'Oreal, and if you say thixotropy control agents, then they will tell you some 10-15 agents. All right, so it is one of them. Now I'm going to take the same material, but now we are talking about slightly lesser concentration. And now we have already formed this particular material. It's already in vial. It's already supporting its weight. So let's see what happens. And it's 2.8 weight%. So it's just little above 1 volume%. Aged sample behaves like a solid. And then you take a rod now and just stir it. I'm not showing you any rocket science, something extremely simple. Close the lid, it floats. Okay. Again, keep it still for a while, it recovers back. By the way, although everything seems to be very simple, over last 2 decades, more than 50 PRLs must have published on this particular topic. Okay, so it's a very profound topic in itself, although these experiments are very simple. All right. Okay, so this is, okay, so what's happening? Again, it's very simple. Let's say you are rapidly kind of shearing the material at very high stress. You drop the stress. When you drop the stress, material has ability to build structure. Its viscosity increases. When its viscosity increases, shear rate decreases. On the other hand, you have rapidly, again, you have applied some stress. Now you have increased the stress, because of which there is structural destruction. Viscosity decreases, and since viscosity is decreasing, your shear rate is increasing. This is the simple phenomenon of thixotropy. All right. Now what happens is that now let's take a material. All right. You are shearing it at very high stress, and you wait for a certain period of time. Okay, for these experiments that has been done. Again, this is Laponite dispersion, slightly higher concentration. And then you subject it, for this history, you subject it at different values of stresses. There is a threshold stress below which the structure destruction occurs. There is a threshold stress above which structural buildup occurs. All right. When structural destruction occurs, you have, for all those stresses, shear rate increases and it reaches a plateau value. This is steady shear flow. All those stresses below which structural buildup occurs, shear rate eventually goes to 0 and material becomes solid even though it is subjected to a stress. Okay. This particular behavior is known as viscosity bifurcation. All right. Keep in mind that this is shear rate. Stress divided by shear rate is viscosity. This simply means that there is a threshold stress which is mentioned over here as 7 Pascal. For stresses above 7 Pascal, viscosity continuously decreases and you get a steady flow. For stresses below 7 Pascal, you always get a stoppage of eventual stoppage of flow. So it's a viscosity bifurcation, and the corresponding threshold is now also called as yield stress associated with viscosity bifurcation. Keep in mind, this yield stress is different than the Bingham yield stress that we talked about, because there is deformation before this yield stress was applied. All right. So this is thixotropic yield stress now. All right. And this yield stress doesn't remain constant. All right. So if I carry out, so rather than 50 minutes, if I wait for 100 minutes, if I wait for 2 hours, I wait for 10 hours, then this threshold stress will go on changing. Initially it remains pretty much constant, very weak change, and then it starts increasing. Okay, so viscosity bifurcation, but time dependent yield stress. Okay, the material is restructured in such a fashion that that yield stress is increasing as a function of time. Okay, this system shows very peculiar behavior of shear banding. Okay, typically if you are, let's say there is a stationary plate, and if the top plate is moving, then in a limit of steady state, you know that the velocity always has a uniform profile. By the way, this is simple shear flow where the stress is constant across this particular entire shear flow, and there is no slip boundary condition over here, and there is no slip boundary condition here, and there is a linear profile. This is a typical observation. Under certain shear rate range, what happens is that what you observe is you find that material is not flowing for a certain length scale, and then in a thin layer it starts flowing. These results are not from my group, but these are again on clay suspension group. You can see that closer to the wall there is no velocity here, but there is velocity in this tiny region, although the stress is constant. Stress for this as well as this is constant. All right, a very peculiar behavior. If you are using such material in industrial setup, this is an extremely important situation, because industrial setup means heat transfer is occurring, mass transfer is occurring. You have a certain plug over here and certain part is flowing. You must know how to control that. All right. So although these are very interesting physical behaviors, they have very serious industrial implications. Stress relaxation. Well, my talk is last, but I'll still complete in time. So what you do is now is that you, let's say continuous shear is going on and you stop that continuous shear. All right, continuous flow is going on and you stop continuous flow. When that continuous flow stops, obviously stress in material relaxes. All right, but in this class of material, the relaxation of stress may not be complete. Okay, it may lead to residual stress. Again, residual stress is another shade of this particular thixotropic material. Recently, just this year, we observed this very phenomenal kind of observation, and that is stress decreases and then it again starts increasing. I could not publish this result because people told me that it violates second law of thermodynamics. So we had to first prove that it doesn't, and then we had to show that, well, this indeed is a real physical behavior. First stress first decreases and then starts increasing. Another shade of thixotropy. Okay, so origin of yields. Okay, since we are pressed with time, let me just say, so bottom line is that what differentiates between the yield stress fluid and thixotropic fluid? Keep in mind that both the kinds of fluids are out of thermodynamic equilibrium fluids. All right. Whenever in any out of thermodynamic equilibrium system, you have thermal constituents which are overcrowded, you get thixotropy. In any overcrowded, a thermal constituent soft material, you get yield stress. Okay. When you have a thermal constituents, system for all practical purposes is dead. It's not evolving. All right. But in thixotropic materials, since you have thermal constituents and system is out of equilibrium, it has no chance. Thermodynamic compulsions will make it evolve as a function of time. So as a function of time, evolution means structural buildup. Under shear, destruction of that structure means you are getting this reduction in viscosity. Okay. So that essentially differentiates thixotropy and yield stress, regular yield stress fluids. And as far as their modeling is concerned, you consider something like a simple lambda parameter. So this is a phenomenological modeling. Lambda is a conceptual dimensionless measure of structure. And then what you say is that rate of change of that structure, conceptual dimensionless measure, it has two terms: thermal motion induced build-up, shear induced breakdown. In addition to this, you have this lambda, which is measure of structure. You relate it to a certain property of your constitutive equation, like viscosity over here. If you're talking about viscoelastic material, then you have to take modulus along with it. And then you have a constitutive equation. You add these three things, which we do in a very simple setup. I'll not go through these equations again. We get these types of curves. So for certain cases, we get monotonic curve, non-interesting, boring curves, typical Newtonian counterparts. Then we get, in some cases, we get this constant plateau over here. They resemble yield stress fluids. But the amazing thing is that in certain cases, we get this negative slope in the limit of low shear rates. This negative slope is the one that makes all the wonders. And this negative slope, so if you have that negative slope embedded in your modeling approach, it essentially predicts all the shades of thixotropy that we talked about. All right. So if you are in this particular region, then material, so when there is a stress shear rate negative slope, it cannot sustain steady flow. Material bifurcates in two regions. One region remains stationary, other region flows with this particular shear rate, and you get shear banding. And we also do pressure flow with this, and what we observe is that when we apply shear rate in this particular region, we again get pressure fluctuations. Now I just want to leave with one thought over here, that negative slope in the limit of low shear rates is a transport property. It's a materials constitutive property. Observation of flow fluctuations and flow rate fluctuations require material to be compressed and then decompressed, which means that its isothermal compressibility needs to be such that it allows that. Keep in mind, this system has 98-99% water. When transport property becomes non-monotonic, can thermodynamic properties also change or not? Don't know that question. I want to leave this as an open question over here and end with concluding remarks. I'll not take more time now. Essentially, thixotropic materials are thermodynamically out of equilibrium materials that show wonders, and we use them in our day-to-day life. Thank you.
Thank you. Thank you, Joshi, for that wonderful talk. A few quick questions. Yeah. One.
I don't need a mic. So I just want to know, you said a lot about, you brought up the issue of consistency with thermodynamic equilibrium, but when you wrote down a model in terms of that abstract parameter lambda, it wasn't clear what aspects of that model are constrained by a requirement that at infinite time the system, obeys equilibrium statistical physics.
Okay. So
otherwise it's unconstrained. You can write lots of models.
Yeah. So this lambda is a structure parameter. So, well, since it's an abstract parameter, the way I defined it, its maximum value was infinity, its minimum value of 0.
Okay.
So you can actually consider, and I'm talking in a very loose way over here, because we have also done its proper thermodynamic modeling also, but you can consider free energy to be inversely proportional to this 1 over lambda, which means that as lambda tends to infinity, free energy minimization occurs. It's a reaching of thermodynamic equilibrium. And then you relate your transport properties with respect to this lambda, which you can consider to be related to free energy. So viscosity is that instantaneous free energy of that particular state.
Okay.
Or modulus is free energy associated with that state. Okay. Now, of course, there will be, depending upon region to region, there will be differences, there will be distribution, all those aspects are there. A very simple way of capturing that particular observation.
I see. I had one other question. These experiments were done in capillary or in vials of a given size. Does this yield stress state work for more or less any size of container that you have, or is there a scale beyond which it doesn't hold up?
You want to say in the capillary or
in the lateral scale in the capillary, in your vial, for example? Are these properties all true macroscopic properties?
Yes. So see, the requirement is as follows. The requirement is that the shear rate should be in the low region where the negative slope is. Okay. So if your capillary size and flow rate is such that shear rate is in that region, it will work.
I see. Okay, thanks. I'll ask you more questions later.
Sure.
So I have a naive question. So these are properties of materials, as I understood. So there are 50 minutes and how much of stress, etc. These are molecular properties of the material? Would you be able to predict certain, the 50 minutes, how it's going to behave and all of that, knowing the molecular properties of the material? And then if yes, what molecular properties would you need to know?
Yeah, so usually I charge a lot to predict these things. And I'm not joking, because industry demands these questions. If I'm, let's say, producing a toothpaste, then how long that toothpaste is going to remain in a flowable condition is an extremely important question for them. And toothpaste is not the only thing that, well, is in a paste-like situation. Okay, so by carrying out some accelerated tests, you can actually predict. Doing from molecular mechanisms to prediction, we are not yet there. The charging is in a jovial way, but yes, it's a very important question for industry.
One last question.
At the molecular level, it looks as though it is largely hydrogen bonding, especially because we have this unusual property for materials which has large water content. If you go from 0 to 4 degree, we already have the abnormal behavior. So that size changes or stress changes could be due to the solvent. So if you change the solvent, go from water to hexane, these might disappear, right?
No, but see, it's not materials. I mean, there are several kinds of materials. Even water in oil emulsions can show these kind of behaviors. Okay, so I'm talking about class of materials, showing just these examples. The forces at work can be electrostatic, hydrogen bonding, hydrophobic interactions, hydrophilic interactions, all these kind of forces can be there. And many oil-based systems show this behavior. So there is nothing specific about water-based.
Thank you. We thank again Joshiji for the wonderful
Thank you so much.
talk. And we are coming close to winding up this 4 inaugural sections, talks, which were so well seamlessly went. I was fascinated. Jagdish and Joshi talked about toothpaste without talking to each other. And so how seamlessly they went from shock waves to thixotropy. It's a great thing that wherever we saw chemistry, and that made me very happy to chair. The time was on the spot, 12:55, and that was possible because of speakers, not for me. I never interfered. Thank you very much for the Academy for making me chair for this session. I enjoyed, continue to enjoy, because there is basic chemistry of chemistry and physics. Thank you.
Thank the chair and all the speakers for their wonderful, insightful talks. The session now is adjourned for lunch. We reassemble at 14:30 hours. As many of you may wish to walk, the venue of the lunch is the lawn of the main guest house. It is well within the walking distance. Those of you may require transport, the buses are available on the right side of the building. Please do join us again at 14:25 hours. Thank you again.